exploring in front of us. Once again, happy 15th anniversary to come.
Hello everyone, I am Anil Pathak. I was associate with Carbon Lab as a postdoctoral researcher. I stay in the Carbon Lab almost 2 to 3 years. We had a memorable time in the Carbon Lab, particularly Sri Sainam visit, 10th year celebration of Carbon Labs. Also, we have the programs. Also, we have the good discussions, scientific discussions, which gives us the fun moment also and give the learning also. I'll say that keep that learning with the fun. And overall, I will wish the Carbon Lab for 15th years completions. Thank you.
Hello everyone, I am Dr. Poonam Rani, PhD graduate from Carbon Laboratory, batch from 2018 to 2022. My time at Carbon Laboratory was truly one of the special and memorable phase of my life. It was never just about the research, it was about the discovering myself, growing with amazing people and creating moments that still bring a smile on my face. I have so many beautiful memories of Carbon Laboratory, organizing conferences, celebrating lab days, and of course, long work update meetings that somehow turned into the moments of learning, laughter, and bonding. The energy and togetherness we shared truly defined the spirit of our lab and shaped us into the better researchers. I truly missed those days. I congratulate entire Carbon Lab family on completing 15 wonderful years and wishing many more years of success, innovation, and inspiration. Thank you.
Hi, Carbon Lab. Congratulations on Crystal Anniversary celebrations. I'm Dr. Kishore, working in International Iberian Nanotechnology Laboratory. I was a part of Carbon Lab during 2021 and 2022. I worked as a postdoctoral researcher in the area of gas sensors and energy storage devices. My expertise was carbon nanofibers, which are freestanding. I had a very great experience working in Carbon Lab and with Chandra Sharma sir. He encouraged me very well in my career, and it launched me to greater heights after working in Carbon Lab. I wish all the best for all the Carbon Lab fraternity and all the members of Carbon Lab. Thank you.
Hello everyone. I hope you are all okay. First of all, I would like to thank you for giving me this opportunity to make this for this special occasion where Carbon Lab is celebrating its 15th remarkable year of excellence. It has always been a privilege to be part of Carbon Lab family. Carbon Lab has played a very big role in shaping my career since my master's. During my engagement at Carbon Lab, I had opportunity to learn from everyone, every single member of the lab, starting from Chandra sir. And I will always be grateful for your support throughout my journey. It's very unfortunate that I cannot be there with you today, but please bear in mind, I will remain deeply connected to all of you. Wishing you a very good journey ahead, and I hope to see you all very soon. Until then, keep signing, keep smiling, and keep learning. Take care.
Hello, Carbon family. This is Akanksha Rohela. I was a PhD student at Carbon Lab from 2018 to 2023. And now, looking back at my time in the lab, something that I really cherish and I really miss is the way we all worked together for everything. Be it the mock presentations that we all had before before any of our major presentations, the festivals that we celebrated together, and the way we organized all the Carbon Lab events and the conferences that we organized. It really showed the team spirit that the whole Carbon Lab has. But the two things that I really learned at Carbon Lab are it's obviously very important to do great research work, but it's equally important to be able to present that work to all kinds of audience. And the other thing that I learned is the collaborative nature, the way everybody is working with somebody be it outside the lab or inside the lab, the way everybody work in collaboration. These two things are something that is still helping me a lot in my corporate research. And so I'm really thankful for it. And something that I've always admired about Chandra sir is his dedication towards his work, his dedication to take Carbon Lab to new heights in every possible way. And the celebration of this 15th year is just proof that how everybody in the lab, and especially Chandra sir, works to make this lab great. So congratulations to everybody, and I wish all the success in the world to the lab. Congratulations.
Hello everyone, my name is Ashish Priyam Goswami. Currently I am a joint PhD student of IIT Bombay and Monash University, Australia. I had the privilege of completing my MTech project under the joint supervision of Professor Chandra Sharma sir and Professor Murtika Khandelwal ma'am as a part of Carbon Lab and Polymer Lab of IIT Hyderabad. So being part of this incredible group has been truly an enriching experience for me, and I feel extremely fortunate and grateful to have contributed to its journey. So on this special occasion of 15th anniversary of Carbon Lab, I extend my heartfelt congratulations to each and everyone who is associated with this wonderful family. So wishing the lab continuous success and many more milestones in the coming years.
Hello everyone, this is Y. Nikleshwar Reddy. I worked as a project research scientist with Sharma sir in the year 2024. First of all, I would like to congratulate Sharma sir for successfully completing 15 years of this Carbon Lab. Even though my time in the lab was very short, it left a beautiful mark on me. The warmth with my colleagues, the quiet moments of discovery, these memories stay with me all the way. Moreover, I could not forget the Vizag trip. That was the trip where we got to know each other deeply. Thank you, sir, not just for your leadership, but for your kindness, your belief in people, and the environment of growth you have created. And I congratulate once again for your 15 extraordinary years. The legacy you have built does not continue, it lives in us. I miss you all, and thank you. With lots of love, signing off, Niklesh.
Hello everyone, I'm Sheikh Uksana. I worked in Carbon Lab from the year 2020 to 2025. I was a PhD student and graduated in year 2025 May. I worked on gas sensors under the guidance of Dr. Chandrasekhar Sharma and Dr. Mahesh Kumar from IIT Jodhpur. The most cherished moments of my life would be to celebrate tiny occasions with my seniors, to go on tiny breaks, coffee breaks with them, and to celebrate all the small occasions till the large ones like festivals with them like a family. It's great to see that the Carbon Lab is celebrating its 15 years. And I wish all the juniors a very good luck and to celebrate the lab's occasion and to be harmonious in the lab and to reach the greater heights. Again, wishing everyone a 15 years anniversary.
Good morning, everyone. Welcome back to day 2 of Crystal Year celebration of Carbon Lab. Carbon stands for Creative Advanced Research Based on Nanomaterials, Carbon. I'll not take much time. Today morning, I'll invite Professor Chandrasekhar Sharma to kindly come and give us a briefing about yesterday's day and as well as give us a brief outline of what is happening today and a brief background on the history of carbon.
Good morning, friends. Respected Professor B.S. Murthy, Director IIT Hyderabad, Professor Ashutosh Sharma, my guru and mentor, esteemed speakers, colleagues, alumni, collaborators, students, and friends. Very good morning to second day of this C15, the Future Carbon Summit, celebrating 15 years of Carbon Lab at IIT Hyderabad. As I mentioned yesterday, this is not just a conference, this is a celebration of the journey. What began 15 years ago as a simple idea to ask meaningful questions has grown into a vibrant ecosystem of people, ideas, and impact. It's an absolute pleasure to express my deep gratitude to two very prominent people who shaped this journey and who are also present today in this gathering. First and foremost, I would like to acknowledge my PhD advisor and mentor, Professor Ashutosh Sharma, whose guidance continues to inspire my approach to research with a purpose, whose guidance has shaped not just my scientific thinking, but also my approach to building research with purpose. His influence continues to guide this journey even today. I would also like to acknowledge our present director, Professor B.S. Murthy, for his continuous encouragement, belief, and the motivation towards the research excellence and perseverance. His support has been instrumental in sustaining both momentum and ambition in our journey. I also thank my colleagues, collaborators, alumni, and students. You are the true strength of this journey. Over these 15 years, we have achieved several milestones in research, innovation, and training. With 180 publications, close to 6,000 citations with an H index of 43, 23 patents filed, 6 are granted out of them, 21 PhD students are graduated, and we executed 21 projects of worth more than 23 crores. But more than numbers, what truly matters is the people who have nurtured and the impact we have created together. We have trained more than 100 students in the last 15 years. We have always believed that science must go beyond discovery. It must lead to impact. This belief is reflected in our summit theme, Crystal, which is also coinciding with the 15th year Crystal anniversary. So here the Crystal means carbon research, yielding the sustainable technological advances for life. Now, as we reflect and renew, let me also highlight some powerful takeaways from the day one. We had Professor U.B. Desai, our founding director, who inspired us to work on a grand challenge problem for the next 15 years. Professor Narhari Shastri, our Dean Research, he reminded us that we should also learn how to celebrate our achievements. Dr. Tata Rao, my long-term collaborator, he shared important futuristic research directions, urging us to think ahead. And Dr. R. Bijay, Director ARCI and the chief guest of the yesterday's inauguration program, he emphasized on the stronger collaboration and reaffirmed his commitment to support the future efforts between ARCI and IIT Hyderabad. These messages are not just reflections, they are directions for the future. As we look ahead, the next phase must focus on scaling the impact, designing the research with translation in mind, ensuring meaningful contributions to the sustainability. Because the true success of science lies not just in what we discover, but in what we enable. Let me conclude with a simple thought. What began as a question became a journey. That journey became a community, and that community now has the responsibility to shape the future. With that, I warmly welcome you again for the second day of the C15 summit, and I hope that we will be continuing our engaging discussions, meaningful connections, and inspiring ideas.
Thank you, Chandra. So for this session, we have gathered here where our special guest is Professor B.S. Murthy, Director IIT Hyderabad, and which will be followed by a plenary session from Professor Ashutosh Sharma. It is my pleasure to invite Professor B.S. Murthy to come and address us and welcome. I request Professor Murthy to kindly come for an address and inspire us further on this journey.
Good morning, friends. Delighted to see Professor Ashutosh Sharma, who not only mentored Chandra, but mentored the whole country in terms of being a DST, occupying a very important place in DST, and also as a professor of IIT Kanpur, inspiring a lot of people. This inspiration is very, very important. I recall when Chandra is talking about 1986, when I entered IISc Bangalore, first lecture of Professor Ranganathan, I was flat. It was kind of a love at first sight, as people talk, young people. I was also very young that time, so I can possibly use that statement at that time. So immediately I asked my seniors, I want to do PhD with this gentleman. And they said, it's not easy. Professor Ranganathan takes only one student a year, and he should be topper of the class that he teaches. So I worked very hard, became the topper of the class, and got the opportunity to work with him. And as Chandra said, he was the one who told what it means by quality of research. I know that there is a panel discussion that's going to be there, which is talking about quality versus quantity, and quantifying the quality and qualifying the quantity, whatever way you want to look at it. What is important, as Chandra pointed out, is are we making impact? Sorry, these fellows have to be switched off. Yes, give me a minute before I switch off this fellow. So very, very important topic that you are all discussing. And as you travel a distance of about 15 years, which is a reasonably long distance, but a distance which also reminds you at the middle of the journey, that gives you a chance for you to look back. How did this journey go? Did this journey have any purpose? And is that purpose reasonably fulfilled? And re-look at yourselves and start seeing it, what is going to be my future? How am I going to shape my future to strengthen that purpose and remind myself of the purpose once again? It's important to remind these things almost on a daily basis. A life without a purpose is no life at all. Okay, so I think all of us know this. Even particularly sitting in India, which is a place for spiritual, growth of people. Life without purpose has no meaning, and particularly for us who are researchers, there has to be a purpose of whether my research is making an impact or not. And that is something which Chandra is doing it now, looking back that 15 years of his journey. I am sure it must have been very tough journey. This is true with every researcher. Now 35 years into research, I can look back 1992 when I landed at IIT Kharagpur. And incidentally, how many of you know December 6th of 1992? Yeah, some of you know, old timers will know. Okay, that was the day Babri Masjid was brought down. So I landed in Kharagpur on a Sunday. That was a Sunday by 10:30 by Coromandel Express, and then 12 o'clock this news that Babri Masjid was brought down. And then the only person that I knew in Kharagpur was one Professor Pabi. He immediately rushed to the guest house by 12:30. He said, Murthy, let's quickly go to the tech market and buy certain things for you, because next 2 days there will be nothing here. Everything will be closed. And I exactly saw what Bengal is on that day. The next day was Bengal Bandh, one red flag, the impact of a red flag I could see. And then the next day was Bharat Bandh. And after 2 days on Wednesday, I could join the job. But I can see when the department was closed by 5 p.m., nothing is open after 5 p.m. And I had to go to the CSO, Chief Security Officer, and ask him, I need a key. He said, why do you need a key after 5 p.m.? I said, research starts after 5 p.m. Okay, until 5 p.m. I am only teaching. I have come here to not just teach, but I wanted to do research. And then he said, okay, are you willing to take care of the whole department? I cannot give you one single key of your lab or something like that, and I will give you the whole key bunch. I said, yes, I will take the responsibility of the whole department. And that is how, day after day, by 5 I go and pick up the whole key bunch of the department, open the department and start working. And at 3 o'clock in the night, we, with my students, whatever little number of students that I had, we used to go for a cup of tea, and life started like that. I'm sure Chandra's life also would have been like that, starting in the ODF, where nothing more or less existed excepting a few sheds, where you started dreaming of the future, sitting in those sheds. And those are the real dreams, I would say. Particularly for youngsters, I want to tell you, friends, because you have now labs where everything is possible, more or less. And some of us who started life were labs where there's nothing. Until 12 years that I lived at IIT Kharagpur, I did not have a lab of my own. Okay, there's nothing called B.S. Murthy's lab there. And then we had to find out who is compatible, and whatever equipment that we bring, keep talking to them, requesting them, can I put this equipment here? And then some agree, some do not agree. So with all that, making friendships. Now Chandra has a reasonable friend, some of them I see here. So, and it is these friendships that really make your journey joyful, and also make you start thinking that it is possible to do great things together with people. And that's, I think, I'm sure, if Chandra looks back at his journey, it is those collaborations which stand out. I'm a strong believer that growth is only possible through collaborations. While individually we should have a commitment, but individually we can only reach to a certain extent. And collaborations bring so much of synergy and make 1 + 1 significantly greater than 2. And I'm sure his journey of these 15 years had such wonderful collaborations who stood with him, who traveled the journey with him, and I'm sure there are many more who will come. He is very young still, and I am sure 50 more years is there ahead of him. This is just 15 years. I would like to see 50 more years of celebration. Wherever I am, if I am living, I would come when you are going to have your golden jubilee of your group, if I am living. But I am sure that with this kind of passion that he has, and the kind of perseverance, that's very, very important in life. It's easy to give up. Again, many youngsters sitting here. Yesterday, I was in Berhampur, Berhampur. I was talking about some research which I did during my PhD days, and then was trying to tell them about something called quasi-crystalline research. Has anybody heard of quasi-crystals here? Okay, yeah. Some of my old friends, of course, youngsters. So 1982, there's a gentleman sitting in Caltech, looked at a crystal in an aluminum alloy and saw a diffraction pattern which showed a 5-fold symmetry. And 5-fold symmetry by crystallographers was considered to be a forbidden symmetry, and a symmetry that should not exist in a material because it is not compatible with a translation symmetry. A crystal has always been defined as something which has both an order, which means a symmetry, and also a periodicity. Both of them has to coexist in a material to be called as a crystal. He started calling it, because it does not have a symmetry which is acceptable symmetry, he called it as what is called a quasi-crystal. And people went to the extent to say, Linus Pauling, very famous chemist, said there are only quasi-scientists, there are no quasi-crystals. So that is the kind of ridicule people go through when you start your research and talking about something which is different from what others think. And then he pursued that. And it took 2 years for him to publish his paper after convincing a lot of people. But what is more important, I want to tell you, he published his first paper in 1984. And 1978, a paper got published from Banaras Hindu University on another aluminum alloy which had again a 5-fold symmetry. Again, nobody believed. And in India, typically, if your guide does not believe you, you don't move forward to a large extent. Okay, so this is something youngsters sitting here. You must be having brilliant ideas. Okay, do not even tell them with your guide once in a while. Okay, better you do an experiment and get a great result. Today evening I am going to meet. Just now my student called me and said, "Sir, exciting result I have." I said I have to. I am running to Chandra's meeting, so I'll come back in the afternoon. I'll see you. So that's what always for a professor like us makes us feel happy. And unfortunately, Professor Suryanarayana that I know, Professor G.V.S. Shastri, two great personalities whom we know, we respect a lot now. They were all PhD students, but they could not continue that. Just because Professor Anantaraman did not believe that quasi-crystals do exist. And finally, we lost a Nobel Prize which Dan Shetman got in 2011. So what I am trying to tell you is believe in yourself. That is something which is the quality of great researchers. Professor Astosh sitting in front of us, and Chandra is an example coming from that lineage. We always talk about lineage, right? In India, we talk about Gotra. So this is the Gotra that he is following. I'm sure 100 people whom he said, they have all gone through his lab. They own the same Gotra and follow it. And this lineage should believe in yourself. When you believe in yourself and do not bother what others talk about you, I'm sure one day you will be standing tall and be able to tell people that what matters is perseverance and believing in yourself. And I'm sure Chandra is a standing example of that, and I'm sure in years to come he is going to be a leader, which he already is, and definitely be able to inspire many more people who come along in the way of his journey. And I'm sure that Chandra will one day be known as one of the top 3 or 4 people in the world in this carbon research. Thank you very much, Chandra. Thanks for this opportunity. And I'm sure every one of you in this auditorium, these 2 days, you are enjoying this. And I'm sure you will carry good memories. But what is more important from this kind of events is to strengthen your belief in yourself. Okay, that is something which is very important. I'm sure you will carry that message with you. Thank you.
May I invite Professor Chandrasekhar Sharma to kindly felicitate Professor Murthy. Sir, we are really grateful that you spared out this time to be here. And I would like to mention, in addition to perseverance that you mentioned, there is a multiplier, and the multiplier is the well-wishers that he has got around him, which includes you and Professor Sharma who are here and all the people who have gathered. So, may I also request Professor Ashutosh Sharma to kindly join us on the stage. So this is the time to launch a journey of Carbon Lab captured in a book. It's a coffee table book. So we did launch it yesterday as well, as you all witnessed, but it cannot be complete without it being launched in addition to them with the 2 people on the dais who are important in carving out the shape of Carbon Lab.
I always believe that researchers take more tea than coffee.
So, tea table book. Thank you so much. Kindly stay on the stage. I request Professor Chandra to kindly come and disclose a surprise.
So the surprise is that every year we celebrate the lab day, and on that occasion we always have the best student award for that year. So this year is also not an exception, although it's a 15th year. So this year also we have a Best Student Award, and this time it's a joint award based on the overall achievements and also the last academic year achievements. So I'm very pleased to announce the Best Student Award this time. It goes to, any guess? Dr. Ankit Chaurasia. Yeah. And Dr. Soni Cherian. So both of them recently graduated from the lab in January. And Ankit finished his PhD with the 14 publications, one patent, and most of his publications are in very high impact factor journals, including 3 papers in a small carbon, a small structure. Similarly, Sony, she has 6 publications in very high impact factor journals and also filed 3 patents. Sony is a ARCI PhD scholar. She worked along with the ARCI team and also helped in the scale up of the many experiments she has done.
I was thinking it is 1 lakh. When I carefully looked at it, there's a dot somewhere. It is 10,000. Written 1,000. You should get 10,000. Okay. Otherwise, I come back to me.
Okay, may I now invite all the current students of the Carbon Lab as well as alumni to kindly come onto the stage. All students and alumni are here. What about Hachanai? Okay. Chalo, go forward. Go forward.
We'll keep the chairs front or.
So before we move on to the plenary session, that was indeed a great, sweet culmination as well as commencement of this day 2. We're just setting up here for the plenary talk.
Hey, Chandra. Then it says is a journey of 15 years. Journey of 15 years. So how many people here believe journey is more important than destination? Raise your hands. Yes, you fall right in the trap. So I often discuss, what is it that people believe in and what is it that they say. So there is always a difference between what we believe and what we say. Huh? What do you think? Why do you think that is so? See, we are totally focused on destination, of course. We have to be. But we cannot say we are focused on destination because journey seems more attractive. So I don't want people to misunderstand me. So I say, hey, journey is important. But actually, it's neither the journey nor destination, which is very important. It is the company. You know that joke, right? It is the company, the friendship that all of you exemplify. The company, which is important, is the company paying for the journey, which is important. Arey, laugh, yaar. You guys are sleeping or what are you doing here? Hey, wake up, wake up. Huh? So I'm very happy. I'm very happy to be here with the family, especially family of grandchildren, especially when they're out of diapers. It's very good feeling to be with them. You don't have to nurture them, nourish them anymore. So that's fantastic. And so thank you very much for having me here, Chandra. It's a great journey that you have been having. Arey, why is the light on in my eyes? Huh? You throw some light? Okay. So, like I say, it's fantastic, and I congratulate the journey of 15 years and many more to go. As was pointed out, there are a couple of notes I made from Dr. Murthy's talk. So he said that if he's still alive, he would come back after 50 years. I will actually come back even if I was dead. We have a real magic, you can come alive, then, and then walk. I know the pyramid technology. So, okay, the next thing, he talked about, quasi-crystal. And I happen to note that this conference is called Crystal. So maybe it's time to change it to quasi-crystal and not to miss the opportunity for Nobel Prize in there. Anyway, 15 years is a good bit of time. How do you measure that time? In 15 years, the solar system has gone around the galactic center 1,000 billion kilometers. 1,087 billion kilometers to be sure. So it is a long stretch of time for humans, short stretch of time. You have been able to achieve all this in 15 years. It's a great testament to Chandra's insight, commitment, lot of hard work, and all of you together in this journey and destination and everything. So now I thought, this is related to carbon, this particular thing. So I thought I would talk a little bit, some keywords related to carbon as I understood them some 12, 15, 20 years ago. So these are only keywords. There is no great research which has happened in my lab in last 10, 12, I wouldn't say 20 because 20 is when Chandra graduated. That was the last time some good research in carbon happened, right? So, so I could either talk about this or I could talk about anything else you want to talk about. Let me go through this very quickly. Why do I want to go through this very quickly? Because I sat on these slides last night working hard on them after a bit of gin and tonic, which is a very hard thing to do, to work on slides. But I did it. So I should show you some of this. So carbon, what is most important about carbon? If you were to look at two great problems of carbon, one of them, of course, is created life, but that problem is now behind us. The second one, that the same carbon now threatens to destroy life on planet Earth. So one of the major problems related to carbon, of course, is carbon emissions. And so whether you look at source, bottling at source, sequestration later, utilization, and so on, so many different things which are going on here. The second aspect is, can we convert CO2 into useful chemicals? So that is the holy grail of chemistry. If you do, this is basically a problem of catalysis. So if you solve that problem, having a really good catalyst to do that, then you certainly get 2 Nobel Prizes. So that's the problem really to work on in terms of carbon. All of this hangs on our ability to produce clean green hydrogen, because the carbon problem is intimately related to the problem of hydrogen. I mean, are we able to produce green hydrogen in quantity and with transportation, I mean, taking care of the whole ecosystem of hydrogen. So that is the three big challenges for all of humanity for all foreseeable future: to deal with carbon, to deal with it with clean energy, and so these two things are, their nexus is so strong that one cannot be solved in the absence of other. So let's get on with our journey of carbon, my journey of carbon. Okay, we got it. So let me start. Um, Carbon is remarkable. Atom is graphene, diamond, CNT, coal, and everything organic. From Nobel Prize as for graphene to power plant as for coal without changing his identity. That's impressive because we managed to change our identity between proposals, publications, and press release. So carbon is doing great, as you can clearly tell. I mean, we partake of some of the nature of carbon. So this is where it all hangs. So, as we already know, this is no great surprise that carbon is so versatile. Why carbon? There are only two things which are important in this universe, on which hangs consciousness: water and carbon. Both are very mysterious. So, while people think, hey, this is just another element, this is another material, they're not really that. And so, it's something very unique. Of course, carbon is element, water is not, but equally mysterious. And when they come together, it takes two to tango and to produce life. So here we have graphitic carbon. You all, is there anybody here which is outside of carbon community? Okay, but only a few. So I don't need to really repeat any of much of this. You can read it quickly and you see what I want to look at here, different forms of carbon and different applications that these forms of carbon have. So key applications, of course, they are all applications you can see there. Disordered and amorphous carbon. What happened? Can you go back? Who is changing these slides? Is the control in Chandra's hand? No. Okay. So I think I'm changing it. Okay, I forgot. So okay, the expanded graphite and graphitic foams with a high surface area, good thermal transport. So wherever you need thermal interface materials, EMI shielding as well, absorbents for oil spill. They are some of the very known uses for different kinds of carbons, and lots and lots of research in all of them. When I was associate editor for applied materials and interfaces, lots and lots of papers would come about, hey, I can absorb oil, many different ways. So take almost anything, it'll absorb oil, right? So now you just make a good song and dance out of it, then you can publish it. So there are so many, if you just look at how many papers in EMI shielding, but all of them would pretty much conclude the same. They'll say, hey, minus 20 dB, minus 40 dB in some narrow band of values. Why I'm saying all this is that we often have to not just be incremental about things. So if I take a new carbon material or new form or something, and I produce the same result as the old carbon, there is not great deal of excitement in that. While it is certainly excitement in publishing, but behind it, after 2 days, that excitement kind of not remain until you get the job, of course, based on those papers, which is good. But at the same time, we think about, hey, what can be profound? Can we be little less incremental? Which means if everybody has done in this narrow band of spectra, the shielding, can we go little wide spectrum, maybe 5 times what is there now, and actually minus 20 dB, minus 50 dB, all the same as far as shielding applications are concerned. But because people believe in decimal places improvement, so it looks like minus 20, hey, I got minus 22, so that's great. Okay. So there, of course, disordered and amorphous carbon, black, activated carbon, very good for cleaning up applications. Fibrous carbon, load-bearing carbon, carbon fibers, Carbon composites are very important. So they are looking at defense applications, a whole lot of, composite materials will require high strength. So these are the materials of choice. Nanostructured carbon have become important. The rise of nanostructured carbon is a recent story, as we know. These are carbons which may be 2D or highly confined quantum dots, carbon nanotubes, few layer graphene oxide, reduced geo carbon dots, diamond-like carbons, which have been around for a long time, and they are very useful for inert coatings in many different kind of instruments. Emerging in hybrid carbons, vaccine-derived carbons, now they're getting popular. Then, of course, we know carbon in energy and climate engineering is very important applications. This slide was supplied to me by Chandra, so he can explain it. But I can explain it too. It's fairly simple. So now you see history is named after the materials which are define that particular age and applications. And so there's Stone Age, Bronze Age, Iron Age, Steel Age, Silicon Age. What next? So question is, if so many of these, intelligent people are working on carbon, then we can define that as the age of carbon. Carbon age maybe. So, and within the carbon age, you look at the rise of different forms of carbon. 1985 was very important. Fullerenes were discovered. Then after that, carbon nanotubes. And this is the whole new journey of carbon. It's got whole new breathing space, whole new life in carbon. Because until then, it's becoming a little bit boring. The same old carbon. But then, with these nanostructured carbon, new stuff came in, and new excitement came in, and new funding came in. Okay, so thinking about that, of course, every few years we discover a new form of carbon, and we say it's going to revolutionize everything: energy, electronics, medicine, environment, climate, economy. To be fair, it does revolutionize. It does change slides of keynote lectures and review papers, in addition to many other things. Oh, you got it? Yeah. See, so persistence pays. Oh, you got it. Thank you so much. So why was I saying persistence pays? Because the gentleman said they don't have any collar mic. I said, no, you look around in the entire campus, even if you get it after half an hour, it's okay, right? So remember, persistence pays, even when there is no hope of success. Okay, you must still try, put some balls rolling, maybe they will roll uphill once in a while, can happen. So this light-hearted joke, not to be taken seriously. Of course, our community, most of us, we work in academia. So what is most important for us are the papers, review papers. They get a lot more citations than other papers, so this is good. Okay. So why carbon age? Because a whole lot of stuff happening, optoelectronics, variables, battery, insulation, lubricants, mechanics, sports, all of that based on carbon. So clearly it's an age of carbon. And so what is expected is in 5 to 50 years, this slide may be 5 years old. So we are already there. 5 to 50 years, the birth of innovative products through sophistication of materials. This is a generic thing. So anyway, this will always be there. After 50 years also, you can say this, right? And then, so it's all happening now. Things are coming together, desalinating seawater. Water is going to become a huge problem. So if we find use for carbon for the overarching problems like water, environment, climate change, even AI, I don't see how carbon could be related to AI. But if we can do that, then this would be a very strong coupling. The carbon would find new importance. Of course, we talk about AI for carbon. I mean, AI for taking care of, say, environmental problems and climate change and sustainability. But I don't mean that actually. So AI would certainly degrade sustainability. But that's a different topic, and I will not talk about it now. Where you go there? Is it moving from here or there? moving from here. So, of course, carbon has a big role in sustainability aspects, every aspect of sustainability. And green hydrogen, as I pointed out, is the key. If any hope is there in the horizon at all, then this is all hanging on green hydrogen, its production at a scale and utilization. Now, of course, we talk about green technologies in context of carbon. So if you want to reduce carbon emissions, we need green technologies. So of course, there have been green technologies in last 3 decades, but they have not arrested carbon emissions. So here's the chart for carbon emissions. It's keep going up. The reason is very simple. While the technology, green technology, increases the efficiency of consumption, the efficiency of maybe by 5%, you say, look, if I consume this much, this would be the emissions. So by using a new technology, you have 5% less emissions. But at the same time, the consumption increases more than 5%. So therefore, there's never going to be a decrease in emissions. And now we think about, hey, for some, like 2 years ago, I woke up and said, what about the sustainability of the digital world itself? So I grew up with these emails and stuff from the 80s. So I used to think that this is all free. In place of paper, I'm not using a paper, so therefore the cost to the environment is really not there. But so of course I was wrong. Every email, every query on large language model is melting the polar ice. So it's about 6% of energy consumption today is because of digital cyber world, and this is increasing exponentially. It's estimated that it would probably become half of energy consumption of the physical world very soon. When I say this, people say, how soon? People want a timeline on that. I say, no, in your lifetime. Okay, so that's the only important thing there is. So it's very interesting that it's not only the physical world that contributes to environmental degradation and climate change, but also the substitute digital cyber processes. Because the physical world is more and more dependent on the digital world, and it accelerates the processes of physical world. So, of course, there's other aspects here that not related to carbon, so we skip that. This is my favorite slide. We say, look, in carbon, it's very important to pay attention to nexus and life cycle, because everything in carbon is related to something else. Carbon alone has no meaning. The meaning is got into because of nexus. So anyhow, it says, I used to think that top problems were biodiversity loss, ecosystem collapse, and climate change. He thought with 30 years of good science, he could address those problems, but he was wrong. I should not say I was wrong. I am never wrong. He was wrong. It's a statement. The top problems are selfishness, greed, and apathy. To deal with those, we need a transformation. And we don't know how to do that. So, of course, what scientists don't know how to do, others also don't know how to do. Certainly, politicians don't know how to do, bureaucrats, nobody. So, it doesn't matter. But the whole point is that the problem of carbon emissions and climate change is not only a problem of science and technology. This is something we don't explicitly acknowledge. It's a problem of the heating of environment outside is a reflection of the heating of mind inside. So in the most ultimate analysis, that's what it is, but via different technological processes that this happens. Okay, so this is the last non-technical slide, and after that I'll get back to carbon for what it is worth. But anyhow, so what is the problem of carbon emissions? The problem of carbon emissions, as I pointed out, is not a problem of technology. We can find better technologies, no doubt, but it would not resolve the problem. So what would resolve the problem is our understanding of what the needs of society and individual are. And needs of society and individual are basically represented by this pyramidal thinking. This is called Maslow's hierarchical model of motivation. At the bottom of it are called deficiency needs, which are roti, kapda, makan, or physiological needs, safety needs, belonging, love, esteem. The love is not like Bollywood stuff, right? And there's a different kind of love. That also is needed, no doubt. But okay, so deficiency needs. These are the needs which can be addressed by consuming more, which means technology. So through technology, we consume more, and therefore the needs can be addressed. Of course, there is a threshold for these needs. So while there is certain amount of necessity about these needs, they have to be satisfied to some necessary level. But there is no sufficient level for these needs to be noted very carefully. There is a necessary level, but there is no sufficient level, which basically means that all of these needs you can keep piling up more and more on top of that. If you had 5 cars, you can have 8 cars. 8 cars can have 18 cars. Okay, so there is no upper limit to these needs, but there is a lower limit. So what happens when these needs start to get satisfied more and more, the growth needs kick in. So people start saying, I need cognitive needs, I need to be creative, I need to have these cognitive expressions that I leave in the world. So they say, hey, settle down, write a book. So what is a settle down, write a book is a cognitive need. Okay, write a paper, I want high citations, I want whatever. These are all cognitive needs. They kick in after I have comfortable living. So aesthetic needs, I go everywhere. When I go, I start looking, hey, is it aesthetics? Is it aesthetically balanced? What is happening? Most people don't pay any attention to that. So anyhow, all these needs are there. So now what happens is, in the civilization in which we live, we have substituted growth needs for deficiency needs. So it's a misunderstanding. Basically, we said, look, I don't know what to do about my growth needs. So, but I will pump in more and more in deficiency needs and hope it will spill over to growth needs. Right? This is the assumption, which is actually a misunderstanding, which is a wrong assumption. And that is the reason for accelerated climate change. This is where it comes from. It doesn't come from technology. It doesn't come from anywhere else. It comes from the fact that an American who has 5 cars wants 10 cars. That's basically it. Okay, so now we leave this stuff and I go to carbon. And these are some of the people who have contributed to my understanding of carbon over the years. I think many of them are still in this business. All of this actually started from the seeding done by one gentleman I'm not sure, but Mark Madhu. Right? So he used to visit us. Chandra, when you first started coming to Kanpur? 2004. Yeah, so I was totally dedicated at that time to my thin film stuff. And then this guy was saying, hey, we should do some device. He was a big crusader for carbon devices. I remember. And then his book on MEMS is a classic, followed all over the world and stuff. And then we hit it off immediately because we both believe in gin and tonic. So there's another reason. So one of the reasons for a successful collaboration is not only what you bring on the table. Of course, what you bring on the table is very important. I take back what I said. What you bring on table is very important. Okay. So in addition to what you bring here, right? Okay. So all of these people, have greatly enriched my understanding of carbon. And I think they're all somewhere doing well. And we see Chandra right here. Okay. And then, so Mark Madhu actually, as I said, seeded these ideas in my group and in India. Indeed, many people have gotten into carbon business since then. A lot of credit to them. Carbon credit. A lot of credit to them. Yes. Okay. So carbon MEMS, this is what this fellow Mark Madhu introduced. He said, oh, we can make devices in carbon. Right? So instead of making devices in silicon or making devices in polymer, which are more mainstream, how can we make devices in carbon? So this is where it started, and you can do all sorts of devices, microfluidics. Of course, the batteries, is a particular kind of battery called micro batteries to call them. So basically, you increase the surface area by creating microstructures on the electrode. And so all this stuff which is there, carbon MEMS. So whole question was, how do we create carbon MEMS? So this requires a bit of lateral thinking. And so what is the philosophy? Philosophy is, look, I want to make some stuff in material C, but I cannot make it in material C directly because the fabrication techniques for that material are not well established. So I make the stuff in material AB and then convert it to C. So, don't go for the kill directly, but go indirectly. First, let's say you make something in polymer. So soft lithographies are well known. So you can texture a soft material like polymer, and that polymer contains is a good source of carbon. So if you do pyrolysis, then you would convert that polymer into carbon. So that's the basic philosophy. And you're saying, look, what are the techniques for micro nano fabrication? So it could be photolithography. SU8 is basically a photoresist material, which is also a good source of carbon. So if you make something in SU8 and then do pyrolysis, that you would convert it to carbon structure. Self-organization, micro molding, electrospinning, nano imprint lithography, whole lot of classical techniques for micro and nano fabrication one can use with a polymer and then convert it to carbon structure. And that's the simple philosophy. In that simple philosophy is the potential for 2000 papers, if you would. So it's so simple, but yet so productive, if you would. So these are the kind of ideas that one should look at. A single idea is like Upanishadic idea, just one line, and can create a Mahabharata. Okay. So how do we go from Upanishadic to Mahabharatic is basically represented by this simple thought that you can make things tough in polymer and then therefore convert it to carbon. But of course, a different kind of carbon, because depending on the cooking conditions, depending on the post treatments and all of that, and depending on what kind of polymer that one starts with, all of that basically determines what kind of carbon would you obtain. So one can tailor it in a many different ways, and this is the reason why carbon is so versatile. So even after producing that carbon device, then you can functionalize it in many different ways. This is very good for sensing applications, for example. So I talked about the fact that there are these slew of techniques for micro fabrication. Now we had also proposed a new technique which is inspired by this popular movie of the 80s. It's called Honey, I Shrunk the Kids. So he said, look, you can make up. I should also tell you, how many here know about top-down and bottom-up techniques? Top down, bottom up, everybody knows. And how many of you call it bottoms up? No, nobody calls bottoms up. I've heard many people call it bottoms up. So that's related to a different context. But bottom up, basically self-assembly and self-organization, the bottom up techniques. And then top down is using machine tools, some radiation, some laser, something like that. Do that. Miniaturization basically means that, look, I make something bigger. It's more difficult to make 100 nanometer complex object, three-dimensional. But if I can make 100 micron with micro machining, I can reduce the size. So for example, make that object, then do micro molding with a gel, then shrink the gel by drying, then repeat the process, and every time you reduce the dimension somewhat. And so if you do it 4 times, you reduce dimension by 1 order of magnitude. The technique would be applicable to complex 3-dimensional objects and their miniaturization. Basically, one of the very simple ideas. I think it only took 2 months to complete the idea and publish in Advanced Materials, which was then the top journal of material science. So what I want to illustrate is it's important to have a new idea. It's not important just to use $1 billion worth of instruments to do what everybody else is doing in life, which is not very much. So it's good to have a new idea, no matter how strange it might look, but it can be convert it to reality. By the way, what we do today mostly limited by ideas. It's not limited by technology. So if one had an idea, then it can be converted into technology or product, even if with some struggle. But that's always possible. So never think that, hey, this idea looks so far-fetched. Can it be real? Can it be practical? The practicality comes later. First, one must have lots of crazy ideas. Okay, and then see that many of them can actually be translated in practice. So this particular idea, how is it related to carbon MEMS? So for example, if you wanted to make these structures in carbon for whatever application, these are some microstructures in carbon. So you first make them in a gel. So wet gel, make micro molding or whatever you want to do. Then dry the gel, then it shrinks. Then carbonize the gel, it shrinks more. So basically you are starting, let's say, at 10x. They'll get eventually your carbon structure of the same kind would get reduced, let's say, to 5x. So you will maybe reduce the dimension by one order of, not one order, but something like that. So in fourth cycle, one order of size reduction is achieved. So enough time, suppose you are using optical lithography. Right, the limit usually would be a couple of microns in most of the setups in the country. Couple of microns which are limited by the wavelength of light. So if you want to go down below that, maybe you need some laser tool, you need something. If you don't have it, then this can be used in order to reduce the dimensions further. So these were some stuff which was, I think, made in plastic. They can be converted to carbon. They say the micro mixer, convex lens array, periodic arrays of different kinds, and then array of micro cantilevers. So they make these array of micro cantilevers in carbon. This can be very useful because this can be functionalized and can be used for biosensing. So a small amount of adsorbing molecules in there will change the frequency of vibration of these cantilevers. So this is a known technique, but basically making this stuff in carbon is basically, that's the challenge. Let's look at other carbon story. So one of the students, Kunal Mandal, he was doing spin coating of PAN polymer. Then he found out by serendipity that these films are not solid, they are porous, and the porosity can be controlled by changing the speed, the rotation, by changing the dilution of polymer and many stuff like that. So that one can actually create these porous PAN films, and by carbonizing them, you would create the carbon porous films of controlled porosity of different kinds. They are macro porous, right? So what can we do? We can do a lot of stuff. So it's a one-step process. First of all, we are creating porous membranes or films simply by spin coating and doing nothing more. So it's like self-organization, and after that doing carbonization. So it can be used as catalytic support. One can use it for different applications which are given. Some of these applications we had pursued for these films, but we stopped doing that research in my group. There's still a lot of stuff which remains unexplored. So that's why I'm just bringing out some of the keywords and concepts. If any of you have interest, I'll be happy to tell you the full story. So these were used, for example, as flow-through membranes for electrodes, for catalytic support, and for cell support. Cell support was very interesting application. Perhaps one slide later it would come there and see what can you do with this stuff. So it has pore diameter can be controlled by these parameters. Now, for example, if you wanted to look at behavior of cells on different substrates. Oh, this is painful. Don't know who prepared this slide. Okay, there. So it's a very active area of research to see what happens when you put a cell on a surface and then subject it to electromagnetic field. So you can change differentiation of cell, you can change mobility of cell, you can change biocompatibility, you can change proliferation of cell, all the cell behavior can be controlled. Now this is very interesting because when I started looking at this problem and people want to apply electric field on the cell, and there people means biologists, they know something, okay, that something may not be a whole lot, but anyway, so what were they doing? So they put some cell in the cell culture medium, and then they put 2 electrodes in the culture medium, and then apply some voltage, put some battery outside. What's that going to do? They're going to actually have current flowing through the cell medium. So it's not just electric field that you're applying, but you are actually subjecting the cells to an electric current. So obviously this poor cell is going to shrivel and die. I mean, depending on how much current you are flowing and stuff. And all these guys proudly saying that we are studying the effect of electric field on the cell. So I said, this is completely crazy. And there is no electric field here. So I said, to have electric field, what you need is an electrode on which cell is sitting, and then another electrode outside, okay, outside here in the air, and then you apply some voltage, and then you have an electric field acting on the cell without current. Once you have current, you even have, you have electrolysis going on in these cell experiments. And biologists, you can sell any story. Okay, they can publish them in good journals and stuff without anybody questioning it for a long time. So anyway, the thing I want to convey to you is that just because people have been doing something for 20 years doesn't mean that this is right. We must examine the basic foundational aspects of what people are saying. And it's like this. If a person with a lot of experience in some area, some wise person, recognized to be a wise person, says something is possible, he is likely right, because it's by experience he says it is possible. But if he says it's not possible, then he is likely wrong, because he doesn't have the experience. So he is saying it's not possible. But so one doesn't have to believe if somebody says it's not possible. But you may believe them if he says it's possible. There's the difference. So anyhow, so what did we do? We took these carbon porous films that I just showed you. Take that as a substrate because conducting. Carbon is conducting, and also turns out that this is compatible with cell. So cell, they don't die. They properly function on the substrate. This substrate is biocompatible that we had shown. So then basically you have cell sitting here immersed in the liquid medium, cell medium, and then this is one of the electrodes connected to the outside electrode which is in the air, and then you can apply different voltages so you can vary the electric field which the cell is subjected to. So it is probably, I think, the first time that the experiment was properly conducted. Meanwhile, I made up this. All this stuff I was doing late night. Okay, all this light humor or whatever it is. So carbon is versatile, we say. It behaves and functions differently depending on conditions, pressure, temperature, surface, groups, structure, and the funding prospects and cycles. Right, so it is indeed very versatile in that sense. Okay, so this is what we found. For example, if you put neuroblastoma cells and apply electric field using this protocol, they say, hey, how do these neuroids, they grow out from neuroblastoma cells? Can we make them better? Can we grow them longer by applying electric field? It turns out that yes, you can modulate it, and there is some optimal electric field strength which would lead to the optimal growth of neuroids. This is what these cells do. So, but of course, different cells have different functions. It's another gold mine for publishing. So, I mean, how many cell lines are there? And then, so you just put one, put another, put yet another, and, you can make a good career out of this. Any of you want to do that? I can tell you more secrets about this research. So, anyhow, interestingly, it also turned out that the same electric field which accelerates the growth of neuroids also deactivates bacteria, which is a fantastic news for biomaterials, because biomaterials, we put them in body, they get contaminated, some bacterial growth may happen. So in saying, okay, so we want cell function to be enhanced, but at the same time, bacteria to be deactivated by this applying electric field. Everybody here knows that by applying electric field, you can puncture a cell. This is how actually fusion of cell happened in the beginning. So if you want to transfer the material from one cell to another, you need to fuse them, and you can fuse. One of the ways you can do that is by applying an electric field, so make them porous. So here we did a lot of stuff with this, but okay, you get the idea. Also look at deactivation of different kind of bacteria at the same time as we are accelerating the function of neuroblastoma cells. Okay, let's switch gears. What else can you do with carbon? So, a lot of people are making these platforms for delivering drugs and actives. You can be dendrimers, could be liposomes. Whole lot of stuff is there. Okay, and but when I started working on this in collaboration with one of my biologically enlightened colleagues, Shiv Kumar, right? So I saw at that time that there were two kind of particles that were missing in the literature. One, lo and behold, believe it or not, carbon. I say, oh, why not carbon particles for delivering drugs and actives of different kinds as a container of cargo. But not only just container of cargo, but also, for example, if you want to make these MRI contrast agents or any of these, when you want something hydrophobic to be encapsulated, maybe drug or these particles, you can actually grow them in situ. So suppose you made a carbon capsule, which is porous, and then put some precursor material for nanoparticles in there, then this acts as a micro reactor itself, and then you can create these nanoparticles for imaging, for example, for diagnostics in situ in there. And then so it can be used for theranostic purposes, so both delivering drug as well as imaging in the same vehicle. So how do we do that? Okay, you can make mesoporous carbon capsules and then load them. So you create all these you create an imaging vehicle but also drug delivery vehicle together. You can see there. Multimodal imaging simply means by using two techniques. So MRI and something else to do that, fluorescent technique of some kind. And so here, the cartoon there, and these are the real capsules which are created with carbon. They can also be antibody tagged. Of course, carbon again can be functionalized in many different ways. So what it means is that you can make it seeking a target, a particular target, because they'll recognize a tumor or something like that and attach there preferentially. So it can be functionalized in different ways, as I said, by antibody tag. And it can be used for dual imaging, stuff like that. Then you can also make it near infrared and pH responsive. Why pH responsive? Why do you think we need pH responsive capsules to deliver drugs? Anybody knows the answer to that? Anybody knows the answer to that will get a special trophy. What? See, the tumor microenvironment is basically very acidic. So what happens is, okay, once you get in there and you release your cargo, this is where you want it. So you want anti-cancer drug, you don't want it to go everywhere in the body and kill the person before it kills the tumor. So therefore, something which is tumor specific, then that can be triggered by that. And so these are some examples of that. Then you can also wrap it. This is another gold mine. I only believe in gold mines. I don't believe in one at a time stuff. Why is it a gold mine? Because you can do so many things with it. I mean, we hardly exhausted the tip of the iceberg, maybe 20 papers, but this has potential for 2,000 straight away. Okay, so you make these capsules because you can do so many different things. You can wrap them. Okay, then you make them, because you can heat them. So by localized heating, for example, with NIR, and doing all of that, you can put different drugs in it, different cargoes and different imaging agents, or you can create imaging agents in situ. Especially hydrophobic drugs, they are lost. right? So when you just inject them like that, they get lost. But once they are encapsulated in these capsules, then they get delivered, especially if you have molecules on surface that can recognize the target. So these are targeted, controlled release, and stimuli responsive. So yeah, that's what it looks like. So actually it's a reality, not just fantasy. These pictures just to show, not AI generated, real pictures. Yeah. And then what happens? You can put pegylate them, pegylate or pegylate them. What? Pegylate. Peggy is a better name, I agree. Right. So this again to make them more biocompatible. And so this kind of evolves as a universal carrier for delivery of both hydrophobic and hydrophilic nanoparticles and drugs for theranostics. Really wonderful. I wish more people where we left it, that more of it could be studied. We have studied in animal models. We have studied, of course, in vitro. Now we need some volunteers to inject this stuff there, right? Okay. So what is this? Okay. Oh, we also use these carbon nanocapsules for another purpose. So you can coat them on these surgical instruments. So they also turn out to be antibacterial coatings, and especially you can put some silver nanoparticles in there in these capsules. You can also put antimicrobial substances directly, so there's a controlled release all the time. So it can be both active defense as well as passive defense against bacteria and microorganisms. It was fairly successful in suppressing the growth of bacteria on these coatings. Let's switch gear and talk about carbon nanofibers. So carbon nanofibers, they are made by electrospinning. Everybody knows electrospinning. When we started, many people didn't know electrospinning, but now everybody knows it. And I hope that you have bought a machine from Sandeep Patil's company, right? So everybody knows electrospinning. Have we run out of time? Huh? 5 more minutes is enough time to spin some tales. So electrospinning, right? So, well, I mean, use some polymer solution to make fibers. You can vary their. This one was done by Chandra. That's why I want to show you, right? So I say if you want to create, let's say, multi-modal architecture using carbon fibers. So what you do electrospinning of a photoresist material. So you form actually a uniform mat of polymer nanofibers, which are photosensitive. So after that, you can do photo lithography on them. So you can create all the domains. All the little domains are made up of polymer photoresist material nanofibers. They can then be carbonized to create these structures in carbon. All of this is of, a lot of interest, but again, never followed up. Typically, philosophy in my group has been, you do something for 5 years, then you get terribly bored, right? Then anyway, some people may take it up or not take it up, doesn't really matter. At least I have to look at something new. So here is one interesting thing about wiring up of carbon MEMS. So you want to create a network of carbon fibers or carbon wires which are sticking to different posts. You want to do that because you want to find the IV characteristics of a carbon wire as a function of diameter. So at that time, there are a lot of interest in saying, hey, well, how does conductivity change, for example, with diameter of the wire or with the composition of wire, all of that. And this can be, Mark Meadow said that this stuff can be used as sensors. Of course, it was an exaggeration, but we all, in the first paragraph of your paper, you must write all great things about, what this will do and stuff. It doesn't matter if it does it or not later, but it's important to write our purpose. Sometimes the purpose is met in the long term, sometimes not met, doesn't really matter. It's always stimulating. So what do we want to do? See, so typical way that you steady a single wire characteristics is very tedious. I mean, either you make a wire, then you need a nano manipulator to lift that wire, put it, then fuse it in order to form contacts and stuff. So here we did by self-assembly. Now, what is self-assembly here? So first you did, you see all the little micro posts, these posts which are sticking out. These are done by some lithography. And then you can, some lithography in polymer like SU8, which is a photoresist material. And then you do electrospinning on top of that. So what it does is that all these wires which are shooting out, they themselves go and stick to these posts. So they're called self-assembly. You are not doing anything. See, why do they go and stick there? Because it's just like, you know, this, how you call it, the lightning rod. So lightning rod, it has a very high intensity of electric field on top. So lightning gets attracted there. So same thing happens with electrospinning here on top of the post. So the posts all get glued together and then you can carbonize them. So this whole is a monolith. It's a monolith of periodic array of posts and wires which are sticking on them. And so one can also then can do IV characteristics because you have two electrodes which are addressable. So you can do a whole lot of studies and say how did vary current voltage characteristics and the resistance, how did it change when you have PAN derived carbon fiber or SU8 derived carbon fiber. Basically it tells you depending on the precursor material, you can change the electronic properties of the wire. It also turned out that so depending on at what temperature you cook it, for example, if you add some CNTs or add some metal catalyst particles, you can change the degree of graphitization of carbon and therefore you can change the conductivity characteristics there. So if you add CNTs, what they do is they act as a local template to induce more graphitization around them. And so therefore you change the characteristics. Even more interesting is just the mechanical stretching of these wires by electrospinning. It leads to greater graphitization. Because what happens is the polymer chains get aligned when you're doing electrospinning and stretching. So you see over here that you get this kind of, these domains which are more graphitic, more well ordered. And so you can change the properties of these wires. You can also make hollow and porous fibers. Very interesting because you can load up different things in the hollow part of the fiber. So you get a whole mat of fibers. It can be used for delivery. It can be used as a scaffold for cells. Can be used for many different purposes. Also can be used as electrode in batteries and supercapacitors and all. This is also little under explored area. So it can use hollow carbon composite nanofibers can also change their porosity. There are many different ways of doing that. And so it can be a good candidate material for electrodes. So I'm sure Chandra's group is doing some stuff related to it, but there's a lot of potential there to do stuff. Particle, yeah. So you can load up particles in these fibers. Some pictures of that. Can use it for supercapacitor. You can use it for microwave absorber. All the stuff I talked about. Say, so using these carbon materials, as I said, very versatile. You can use it for many applications. And so my absorber, radiation absorbers is one of those things. Reflection minus 42 dB is considered good. Bandwidth, okay. So here it is. Meanwhile, in actual labs, we're still trying to get the same sample behave the same way twice. How many people have that experience? No? Yeah. Some raise their hands, others don't raise. But we all have this experience. This is comforting because, like life, is consistent in its inconsistency. Carbon is notorious. I mean, we show the best results always, especially in battery and supercapacitor. So when I ask people, hey, did you get it like 20 samples? There are other ones not working, behaving well. Okay. Yeah, okay, so we run out of time, but the whole lot of stuff we did with biosensors using carbon, electrospun carbon, functionalized in different ways, different biomolecules. Now, I've been trying to motivate my collaborators to make biosensor for depression biomarker because it's very, very widespread situation, especially when you're doing PhD. How many are doing PhD here? So wouldn't it be good to actually test yourself at home, right? Saying how much is your today depression biomarker level? Is it going up with the rejection of paper or not? What is happening? So I'm sure somebody will do it because there are now some well-defined markers for depression, and so it can be easily automated. And because people don't like to go to a shrink, there is some stigma attached with that. If you need psychological help, but you can do it yourself at home, then you know that you're having some problem and you work on it. These are all details of different things which are done. Carbon for digital revolution, of course, we know that's very good happening, transistors and stuff which are based on CNT and other carbon forms. Oh, by the way, one of my latest projects, one postdoc just started working on it. They're making a sensor for microplastics. So any of you have interest in that? Yeah, we discussed. Oh, wonderful. Okay, let's get together. Yeah. You see, so there's at least one positive outcome of this talking. Right. So we are going to use molecularly imprinted sensor, and you may have a different approach or whatever, but we can work together. So this all happened during COVID time. So in agriculture, it can accelerate the growth of plants. And these are new forms of carbon which are coming up. And so I should stop here now with this thought. In a carbon conference, our task is simple: to understand carbon and ourselves a bit better. Apply enough pressure to produce diamonds, but not enough to turn weak data into strong conclusions. Okay, so thank you very much, and we stop here. And this is some pictures from the days when I used to work in carbon, but it looks like a pretty good art. This is not a picture. I mean, this is not. I'm saying that this is simulation using carbon material of this, right? And so very interesting pictures. And this is it. Thank you very much. We can have some discussion if you like.
Can I take two questions?
I used to have this joke. People are saying, "What are you working on?" I'm saying, "I'm working on dating carbon." Didn't go very far because of looks of carbon.
Sir, what is the motive behind choosing carbon?
Huh?
What is the motive behind choosing carbon?
Publish papers. Get some money.
Okay.
What do you think? Is there any other motivation for a scientist? Oh, no, I mean, be frank. Tell me. Then I would also learn something more.
So why only carbon? Why not other materials like silica?
Yeah, because I met Mark Madhu. I was doing other things also. So, I mean, why carbon? Because I said, yeah, okay, it just looked attractive. You see, what happens in our lives, if you ask this, it's a very profound question. It's not something to laugh about. It's a very profound question. Why is it profound? Why do we do things that we do? It's very simple, right? Now, there is no unique answer for why we do things that we do. It's just circumstances. If something clicks, something happens, right? And I have no way of predicting what clicks and what happens. It is outside our, this question cannot be answered, actually. It cannot be answered by any known body of knowledge. It's saying why carbon. I mean, all these. Let's get a sample of why people who are sitting here, why they work in carbon. Of course, they happen to join IIT Hyderabad. Then they happen to join a particular group. Then they had no option but to work on carbon. It's just that, so there are many things that happen, and because of which we do what we do. And really, there is no way to rationalize or tell why we do that. But this is a question which requires further probing. Answer would not be in carbon literature.
Any other questions?
So you have been working with various forms and morphologies of carbon, right? And you have been trying different approaches. So from every different approach, you are getting something. And have you ever got a thought, okay, I've got this feedback from this research, this kind of research of carbon, and I can use it in the other, like you have done a lot of categories, right?
Right.
Yeah. So if you got a feedback from one research, and have you ever used it in the other work?
How do you mean, like plagiarized? No,
Not
that's not
like
what I
that.
mean.
See,
See, creativity is only connecting those dots of knowledge which have not been connected before.
yeah.
So do you learn something in one area and then apply it to other area? Yes. That's the only way to do it. So, so like I'll give you a little story. In 1990, I joined IIT Kanpur as assistant professor. At that time, there was no culture of research in IITs. Of course, many IITs weren't even there. But there was no culture of research. They were considered to be undergraduate teaching institutes. They were in my department when I joined. There were 22 faculty members and 6 PhD students. You understand, right? There was no infrastructure. DST gave no grants. They used to give 2-3 lakhs per project and stuff like that. So essentially, these were dark ages of the 90s for research. Now, I was working on something else in the US when I came. So that would have been impossible to do that work in IIT in India in general. I was working at what do you call the stem cells for the cornea, and I had learned good surgery on rabbits. None of which were any use. No PhD student in chemical engineering would join and never find a job doing all this stuff. So I said, look, there's no animal facility, there's nothing. So you can't do that. By the way, in the mid 80s, stem cells were very hot. I don't know if you know the story, the history of stem cells. And, those were the days, very exciting. People said, oh, we don't know the stem cells for the cornea. Why is it important? Because you do corneal transplant. In the corneal transplant, it's very important that the corneal graft survives. Now it will survive if you knew where the stem cells were coming from. Anyway, this is a different story. But anyway, because we could not do that work in India, you couldn't do any work in India, so I decided to be a theoretician. So I said, "Arey, ye sab chodo. We have a brain and we have a computer, and so we can do theory." So now what to do theory? So I wanted to work on some problem. Then my neighbor, who was a very famous physicist, he told me the stuff I'm doing would be of interest to physics community. I didn't know. I had only done physics 101. So I said, I don't know much physics, whatever happens. But I had new ideas only precisely because I was not a physicist. Now, what I'm basically getting at is that you need to don't think like everybody else in the area. So your question was, do you learn something from one area? Do you connect it to the different area? And this is actually in my own experience, the example. So now he said, so I asked him, I said, where do physicists publish? So he said, we publish, if it's a really good paper, you can publish in PRL, Physical Review Letters, which was very hard to publish there. But anyway, because I'm only a lowly chemical engineer, I'm not a physicist, so I don't care what physicists think. Actually, I don't care what anybody thinks. But anyhow, so that means, so I was not afraid to submit there. It got published. How it got published is because I have a different perspective. Not because I'm doing the same thing that all great people are doing. Not only that, I think we could publish about 12 papers in PRL in the next several years only because I was not indoctrinated or conditioned to think like a physicist. Because once you have read 100 papers in an area, you cannot think independently. You should never do whatever other people are doing. 12 papers, by the way, in PRL was more than the entire Department of Physics at IIT Kanpur from its inception. So these people were very, as you can imagine, they were upset. They were saying that they asked me what I said. I got lucky. And never upset your enemies. Huh? That's one thing you should learn. So you should simply say, I'm stupid, I got lucky, and I really don't know anything. That comforts everybody. And then you don't have problems with people around you. Yeah, of course.
Master's in physics. Now I'm researching chemical engineering.
Yeah, come to the right place. No. See, it's always good to know something outside of your area. Okay, and then to bring maybe that connection into something in this community, which is, see, all communities are very strongly indoctrinated. They all have a central dogma. Okay, and so this central dogma is a big problem because people just don't listen to anything. They just say, nee, it must be like that. No, everybody knows it's like that, right? Now, who is this everybody? We don't know. But if you question anything which people assume to be true unconditionally, of course, everything is true, but under certain conditions and so on. But most fun is actually just upsetting people questioning their central dogma. And so for that is necessary that you don't have one to begin with. Okay. And then you say, I don't understand this. So most people don't like to acknowledge their ignorance. They say, nee, I understand. Okay, theek hai, everybody has said it, so it must be true. Yeah. It's like, no, anyway, I would not say what I was thinking. So, okay. So, yeah, what's your next question?
No.
Yeah, good. So use your physics and, do good in chemical engineering. Yeah, go ahead. What?
What biggest challenge you face in your life and how you come out of that?
I have not come out of it yet. Life is the challenge. No, challenge, you see, it keeps changing every year, sometimes every day, every month. How you define challenge?
In terms of research, doing research.
In terms of research. See, when you change area, the first couple of years are challenging. The reason is that you don't know the community. Community doesn't know you. Then you have to go to their conferences, right? Then there'll be a different set of bunch of people and different things, different nomenclature, different dadas, local crowd. No, okay. So this is all a little challenging, but it's also, every challenge is also an excitement, don't forget. So it depends on, it's not the question of challenge, it's a question of how you take challenge. Whether you even recognize something as challenge. See, problem is when we recognize something as challenge, that brings its own dynamics. A human mind is always looking for a challenge and a solution. Now, what I'm asking you is, I don't know the answer. Is it possible to live without it? I mean, why is everything a problem, right? Especially for males. Everything is a problem to be solved. Okay, I don't know. There is some little difference between how different people think about things. But as soon as, my wife states something, I make it into a problem. Then I go about solving it, right? So this is one way to deal with life. You say everything is a challenge, everything is a battlefield, everything must be solved, everything must be optimized, and all that stuff, right? So this is one way to look at it. Other way is, hey, it's life is going on, it's continuum. You have fun day to day, and I don't know, the challenge will sort itself out. What do you think? What is the challenge? I am not, no, I really not thought about challenge. I remember one thing. while moving from US in 1990 to India was a challenge. Because the challenge of a different kind, not research. But you see, challenges are all of this, I mean, inherently they are of the same nature, whether it is in research, whether it is in other aspects of life. Because let's say, you say, hey, there is no telephone. There was not even a cooking gas, right? Because in those days, license Raj. So you say for 3 years you wait for cooking gas, or you can pay bribe. Now I didn't want to pay bribe, which means we wait 3 years for cooking gas. I could afford the bribe, but I didn't want to. So that can be thought of as challenge, but you don't think of this as challenge. You think of this as an opportunity to use solar cooker, isn't it? So solar cooker is a whole lot more fun actually to cook in. You get better cooking, more healthy cooking than what you do on gas. So I don't think I've answered your question, which is a good thing. It's a very challenging question. Anybody else know how you deal with challenge in research? So maybe I'll also learn. Why only need to? I don't need to answer all the questions. You also need to answer them, no? Table, bring it on table. Anybody will offer one insight very quickly about you. Define what you consider to be challenge in your life and how do you solve it. I'll then give you a very quick story. I now remembered one challenge. So when I joined here, then all my colleagues were also my earlier teachers. Because I did BTech there, same place where I joined. So everybody there was my colleagues, became but my previous teachers. So they all wanted to give me a lot of advice about how I should run my life, what research I should do, and so on, according to their idea of what should be done. And you will find in your life a lot of people would be telling you, you should do this, you should do that, you should get married. Are you married? No? So they'll be telling you. Not only they'll tell you get married, they'll tell you who to get married to also, right? So this is the, I mean, you say, why are people around? This is their function, to tell you what you should do. So, okay, so I've been, told all this stuff about what kind of research I should do, where I should publish and all that. So one evening, this very senior well-wisher, he was telling me all this. So I said, look, I have done in 2 years what you did in 20. So he said, what? I said, nothing. This is how you overcome the challenge. Now, a lot of people have told me that things I don't want to discuss, I dismiss them in a joke. Okay. So this can be a good strategy. When you face a challenge, when you want to face a challenge, you don't want to get into discussion of it, right? You think of a joke. Yeah.
Thank you, sir.
सच में बोलो सच. By the way, मन में same है सच में. I mean, people differentiate this for no reason. Reality is both psychological and physical. What? And ontological.
Thank you, sir, for all your talk and inspiring all of us. Now I invite Professor Chandrasekhar Sharma for felicitating Professor Ashutosh Sharma, sir. Now we are moving forward to the next section, that is panel discussion. I request our panelists to come forward.
panel discussion on the topic quantifying the quality, moving beyond numbers in research evaluation. Let me begin with the two simple but important questions that can the quality of research truly be reduced to a number? And are we measuring the research quality or manufacturing it through numbers? For decades, we have relied on various kind of matrices, impact factors, citations, H-index, I-10 index, as convenient proxies for the quality. They are easy to measure, easy to compare, and easy to communicate. They were meant to be the tools, but today they often define the success. We moved from using matrices as indicators to treating them as goals. And when that happens, the system starts optimizing for the numbers, sometimes at the cost of originality, risk-taking, collaboration, and even the integrity. So we must ask ourselves honestly, have we unintentionally created a system that rewards the visibility more than value? This is not just an academic concern. The way we evaluate the research that shapes what problems we choose to work on, how we collaborate, and even how early career researchers define the success. Today, we are in a phase of introspection. Global movements like DORA and the evolving perspectives from academia, publishers, and policymakers are urging us to rethink what do we truly value in research and how do we recognize the contribution, not just output. If not numbers, then what? And how do we ensure that the evaluation system encourages the meaningful science rather than metric-driven behavior? Can we realistically move away from that? This discussion is particularly important for the next generation because the way we evaluate the research ultimately shapes what research gets done. We have with us an excellent panelist representing academia, publishing, and research ecosystems who will bring the diverse and honest perspective to this conversation. I would encourage our panelists to be candid, even if it means questioning the long-standing practices, because the goal today is not just to find a perfect metric, but perhaps to ask some fundamental questions. Let me leave you with one thought as we begin. What we choose to measure ultimately defines what we choose to value. With that, let me invite our panelists to share their thoughts with us today. So Dr. Veda Krishnan from ICAR IARI, Dr. Rohini Ketur from Wiley Publication, she is Deputy Editor for the Small Portfolio, Dr. Diksha Gupta, ACS Director of Global Strategy, and Dr. Gaurav Sharma from the Biotechnology Department, IIT Hyderabad. So I request all the panelists to have their initial perspective on this topic. So for that, may I request Dr. Gaurav Sharma to make a brief remarks. You have presentation?
Thank you very much to Professor Chandra for inviting me and having this wonderful panel discussion. And many congratulations on this 15 years anniversary of working at IIT Hyderabad and being a prominent researcher here. So I will start with a very basic thing, ideally. I will take maybe 2-3 minutes just to present a few slides which we have been doing in terms of research, evaluation, and directions. So ideally we academicians try to publish and obviously make patents, but have you ever thought of publishing any paper that is it really worth publishing? Means, I'm not sure if you guys are listening. I will repeat it once again. Have you ever thought while publishing, means as a professor or as a student, that or maybe after publishing it for 2 years, that was it worth publishing? Okay. Means it can have a very broad range ideally. It can be that yes, it was a wonderful study and yes, that's why we published it and that's great actually. But what I have realized that we are publishing a lot. We don't need to ideally publish that much, and because of all these publishing perspectives, by adding the numbers, by because when you publish more, the quality I'm sure will always degrade a little bit or more. Okay, so the idea is that we are publishing more, and that's why the institutions, the committees, the journals, they all have come up with these matrices, which ideally are not required, and they don't judge very well in terms of quality. They are all working on the basis of quantity and based on numbers. Okay, so that's what what we are trying to do a little bit, at least in this direction. I'm an assistant professor in biotechnology department, so this is not my forte, frankly. Okay, but we started doing it because we keep listening about all these matrices and everything. So I'm a computational biologist, just to say, so I know programming, and that's all we need for making these matrices, right? So data analytics can make smart matrices. Okay, so the point which I thought when we started working on it was more in terms of authorship. Like most of the people, when they talk about H-index, citations, and all these different things related to publishing or publishing a paper, they always talk about all these things. Committees judge people based on H-index, committees judge based on citations, and obviously where it is published. All these things are kind of a perspective, and maybe they determine quality in terms of their judgment. But the main problem which we thought of is that when we are judging it, are we judging based on authorship too or not? I'm sure you must have seen that we always judge based on authorship. Okay, like if you have first author papers, you will get a position, otherwise maybe not. If you have multiple or more co-author papers, then that position will be given to main, like the major person. Okay, so that's why we try to bring this perspective into research matrices, and we have created one tool which we call G Scholar Lens. Okay, it works with Google Scholar, and I'm sure if you have not read about it, you can go to, it's a browser extension. You can directly work in your Google Scholar page directly. Okay. Simultaneously, we are also making another tool which is independent of Google Scholar, where you can directly give ORCID IDs or DOIs, and it will try to define all these different matrices for you in a more contribution aware manner. And that's what I think the point which I am coming from. Okay, that the matrices should be more contribution aware instead of generalized matrices. Okay, just to give you a very quick idea here, nothing more fancy. This is how a scholar profile looks like. But when you run this tool on the same page, it gives a big matrices and big dashboard which will convey all these different things. The few interesting points which we try to convey is that give weightage to your corresponding author, first author papers more. So let's say if some person has more first author papers and more corresponding author paper, they will have less drop in their H index to SH index, which is more contribution aware. But if you have more of co-author papers and very less first author paper which have not received too much of citation, the H index or SH index will drop very significantly because of the contribution weightage. Okay, we also showcase retracted papers on the same dashboard. We also showcase how many papers you have been publishing, how many citations you are getting. Nowadays, I think there is a lot of discussion keep going on in terms of quantile of journals. We also discuss all those things under one umbrella. In case you have not used it, I will suggest you at least go through it and see if it rhymes with your ideology, and if in case it is helpful, that's great. If not, consider it one another tool in the toolbox. It has been very well cited by Nature, by scientists recently. Obviously, there is a lot of positive and negative comments on it, which will always there be. But just to conclude that, let's say if this is one author who has like almost 7,000 citations and 30 H index, but when you run a scholar index, you will get SH index of 18 and HSC citation of this much. You can see the shift here. Okay, the idea is that because this person has more or large number of co-author papers which have got a lot of citations, that's why the drop is. So in this way, these matrices or these matrices, which at least this is our perspective, right? So we will always say praises to that. So it works better, more in a contribution aware manner. So I will not take too much time, but thank you very much and look forward to the discussion.
Yeah, thank you, Gaurav. May I request Diksha to have opening remarks on this topic?
Yes. Congratulations, first of all, for 15 years. And when sir was cutting the cake, I was just thinking, yeah, he had a last week 150 cake cut. Now he is having 15 cake cut. Then Veda was cracking a joke. I wish I had a 1.5 year cake to cut, but she's far ahead of that milestone. Never mind if you don't get that joke or like the fact collection. So thank you everyone for being here. And I really appreciate you bringing that bold topic, because we keep talking about this in isolation in smaller groups. But this conversation is important, and we may not have answer now, but it's important to discuss. So even before we go to tools, we need to understand now what is quality we meant by, and which type of research we are measuring. Because having tool does not mean we apply the tool on everything. Right tool for right thing would give you better results. Otherwise, it could be highly misleading. So when we say quality, it's a multidimensional concept. Are we measuring rigor? Are we measuring reproducibility? Are we evaluating impact, or are we checking the relevance? Once we have a fair sense, then we think about what type of research we are talking about, especially when there is so much push on translation. So if you broadly see research, of course, there are no clear line as such, but broadly you can think of as a fundamental research, as applied research, and as translational research. And once you really understand how each research help you to cater to which need to scientific ecosystem, we probably are better placed to measure that. So with that, I have some notes here that I want to share with you. They are quite factual, so I thought better to use the definition. So when we talk about fundamental research, the goal here is expand the knowledge frontier regardless of immediate use. तो फंडामेंटल रिसर्च में आप ये नहीं बोल सकते कि इसकी एप्लीकेशन क्या है, इसका इम्पैक्ट क्या है, क्योंकि वो गोल ही नहीं है फंडामेंटल रिसर्च का. So when you are talking about fundamental research, so what we evaluate here? We evaluate conceptual novelty. What it means, does it challenge, extend, or reframe existing understanding? Is it a question itself important, what we are trying to answer through the fundamental research? Then we focus on methodological integrity. How rigorous the processes were when we were trying to ask these questions, and the finding we had, are they reproducible, or if someone will validate them, would they fit, help people have the same question and find the answer? And what is really the generativity? Does this open to new questions in that area? Because anyway, we are either challenging the existential knowledge or trying to seek more knowledge. And then, of course, we look at reproducibility potential. So when this is the scenario, we cannot penalize people saying, hey, you have absence of application pathway, because that was not the goal. And also it has a long time horizon. So we even cannot see the impact of the quality immediately, because sometimes it takes decades for a fundamental research to really show the output or the impact of that. And sometimes it's an incremental finding that consolidate knowledge. It may not be the profound knowledge or discovery all the time. Then we get to the applied research. So applied research is something that solves a defined problem using scientific knowledge. We have a problem solution fit. We know this is the problem to be solved, and the problem is defined with the stakeholders in collaboration. So whether we are solving for industry, for society, or whoever, and then we look which are the scientific methods it can help to solve. So here what we try to evaluate is problem validity. Is problem real, significant, and well scoped? Is the fitness of approach? Is the right approach to solve the problem? This is where we expect from applied research. And also we think about scalability. Even if solve the problem, is it scalable? Is it really relevant for stakeholders? So that's why problem scoping is also important, and also it helps some role to contribute to fundamental knowledge, because even if you have a problem solution fit, but it may also give you the new insight which add value. So this is really in between to that fundamental knowledge or fundamental research to the translation. And the translation research is nothing just the deep science, deep tech startup we are talking about. It's really that solution market fit. Even if you asked a question and found a solution, and then you see, would really people need it? Can you really create wealth out of it? Would there be a product need in the market? Would people pay for it? Do we have economic model available? Is there a compliance, regulatory, everything which is outside the science, and you are thinking in a system. So once we understand which domain we are operating, it is very relatively easier for us to figure out which tool we use. So this is this part of what quality meant, and then this is part of the type of research we are operating into. So when you are writing your proposal, when you are going for evaluation, this is also a responsibility to be explicit and very clear the type of problem in which horizon we are trying to solve it or not solve it, right? It gives at least a lens for people to think a little bit more customized. Otherwise, it's easy to have a standard mode on and have, everything talking in the lens. The last point I want to make, whatever matrices are there, they necessarily don't measure the quality, they measure influence and reach. When you talk about impact factor, when you talk about H indices, when you talk about I indices or any metric, they are just talking about the reach, accessibility, and influence. And that influence may not be right. So I pause here and then pass it on to our moderator, Professor Sharma.
Thank you, Diksha, for bringing different perspectives. So I now request Rohini to have her initial remarks.
Thank you, Chandra, for inviting me here. Congratulations on the 15th anniversary of Carbon Lab, and it's good to witness this milestone here. The topic that you have proposed here, quantifying the quality, it's actually a basic challenge. Being from the publisher side, while we talk about the impact factor or even citations and all those things, we have to first understand that few things can be quantified very easily, and there are not everything which has some impact or which has some purpose can be quantified. Okay, so there is some gap, and of course there cannot be one solution for all. Coming to the impact factor, of course I'll talk more about it, but I want to mention here that with the growth of publications overall, people started looking for a very easy tool to quantify, to evaluate the research, and that is where this impact factor, using impact factor to evaluate the research, came into picture. But here is a basic question to you all, to the moderator, to the panelists as well. How many of you think that all the Nobel-winning researchers were published only in the high impact factor journal? Not necessarily, right? Not all the papers were published in the highest impact factor journal. Let's take an example of click chemistry, or the chemist might know it. Click chemistry was, the article by Barry Sharpless, it was submitted to not a highest impact factor journal, but of course a highly reputed journal, Anglo Chemie. Okay. That article, when it was sent out for peer review, it got heavily criticized, heavily. Yet the editors found some significance in that article, and it got published. Now, it has got a Nobel Prize as well. But the interesting point is that the work was so novel that it did not get citations as compared to the other research work in the first 2 years. Later, the citations increase. So what I want to say here is every novel work may not get that attention immediately. The researchers may hesitate or there will be a kind of resistance to adopt that kind of research. So are we going to evaluate the impact of the work only based on the citations in the first 2 years of the publication? No. So citations may not be the right evaluation criteria. Of course, the impact factor, as I said, it did not get published into the highest impact factor journal, but it doesn't devalue the work. And also, I'm not saying that the highest impact factor journals do not publish quality work. They publish it, but of course, what researchers look for, what is the trend, these things matter a lot. And also how breakthrough the research work is and how the researchers adopt the work. These things matter a lot. So not necessarily impact factor or the citations be considered as the complete evaluation criteria. And of course, these numbers are handy tools. They will not capture the complete significance of the work. That is what I want to say. And also, when we look at the research publications, the growing number of research articles, we have to understand that there are some researches which are popular. Let's say, for example, policymakers are putting more interest in, say, energy application work. Okay, these research areas are popular. They are heavily funded, and of course, more number of researchers are working into that field. More number of papers, more number of citations. Of course, such journals may have higher impact factor as well because it's just an average of the citations versus the number of articles published in that area, in that time frame. So, and vis-a-vis the fundamental research, okay, they do have a significance. They do carry some purpose in the research fragment. And if there is a smaller group, research group working in that domain, it doesn't mean that it has got lesser value. It gets lesser cited, that's it. So there again, the criteria can be different. So there is no one solution to evaluate the impact of the work. And of course, one has to look for a responsible evaluation instead of looking only at certain numbers. I think with that, I can pass it on to the moderator.
Yeah, thank you, Rohini. So yeah, you mentioned about that citations may not be the right criteria, and of course, many breakthrough studies they have the impact after many years. And of course, you have given a term responsible evaluation. So I will come to that. So Veda, I will request you for your initial remarks on this topic.
Thanks, Chandra. So first of all, thank you for inviting an alien like me. I think I am the only biocarbon present in this room. So I'm a nutritional biochemist, and my role is to fix the biocarbon through the plants and then to evaluate its role in human nutrition. So that's what I do. That's the only connection of carbon in my case. It's a very important topic, and when I got this topic, I wanted to dissect it, and I want to know first whether we really want evaluation. So that is the first question. I don't know how many of you really want to evaluate your research. And in case if we see all the logical explanation that we are working with the publicly funded money and we are answerable and we need a robust research ecosystem in our country, so evaluation is mandatory. So the next question is like how we fix these yardsticks, right? These proxies so that we can actually have valuable research. So that is the next question. The third question that I think we all are facing is because these numbers are now our decision makers. So the question is whether whatever matrices is, because over the time when we discuss about the number and the journey to optimization is not only affecting we as people, but our organization is affected because there is a lot of evaluation that is happening for organizations and at different levels, right? So it is not a story of impact factor or citations now. So the question is like, these are really the support tools or they are really the decision makers. So I think this could be to an extent benchmarks because these matrices will come and go. It will keep evolving because now even SDG indicators, because as a need of the hour, more matrices will keep on adding, right? But the question is like whether this should be a decision maker or it should only be a supportive tool as an initial benchmark so that we can have a very traditional way of evaluation, and then in the next step what we can do. I think that is the main purpose of today's discussion, that how can we add more layers to this evaluation so that we can have a real impact research or which is really giving potential. So if I can relate to it because I am part of agriculture research, and agriculture is a combination of more than 26 disciplines. And when we develop a variety, any crop, the delicious basmati rice that you relish, when it go to the farmer's field, it is not the publication or the impact of the publication that really works there, right? It is actually the adoption of the farmer, and the farmer adopt, and along with that, the cultivation as well as the field trials and the stringent thing that is happening, the climate resilience and many more external factors play there. So the research which start as a biochemist like me or a breeder who develops a variety, then it reach to the farmer. There is a lot of players in between, and the knowledge dissemination happens to extension workers, and these extension scientists are also scientists and they also want to evaluate, but they don't have these yardsticks of publication or research projects. So I think context specific research assessment is very important. We should not compare apples with oranges, because I think this kind of universal system is, I don't believe that it is the right way of judging somebody's research and somebody's impact in this particular thing. Knowledge dissemination, stakeholder engagements, I think these impacts need to be discussed. And I think my fellow panelist has almost covered most of the points, but I think when we discuss about publication, it's fine. But the research grants, most of the times, I think the numericals that we judge for research grant is how many grants you executed and what is the sanctioned budget. But how can you judge the impact of a project just based on these two yardsticks, right? So I think there are a lot of lacuna in the existing system. I think we are keep on evolving on that. I truly believe today's discussion will come out some more beneficial layers which can add to it, so that we can have more real impact research based evaluation in future. Yeah, that's my initial.
Yeah, thank you, Veda. I think you brought a lot of other dimensions to this discussion. You mentioned about the context-specific evaluation, knowledge dissemination, and bringing the stakeholders' engagement also into it. So let's move forward. So I have some few specific questions before we open the panel for the open forum. So coming back to you, Gaurav, you talk about the author-specific roles in your G-Scholar lens, and you reduce the citation from 7,000 to 2,000, right? Yeah, so now, if this contribution normalized matrix, what you're talking about, it becomes the mainstream, for example, how you see that it will influence the collaboration pattern, authorship ethics, and even the early career researchers' visibility?
So, the main point here is that when we publish a paper or a patent or anything, we always have a contribution thing in our mind, that, okay, oh, this is the main person who is leading this project. This is the main person who is supporting like 10%. This is the person who is doing like 20% of the work. It means the team knows about it. But the problem is that when the evaluation comes, that everything is distributed similarly to all of them. So my main point is that whoever we are collaborating with, the point is that they should collaborate in a significant manner if they want significant, significant part from the output. Okay, if we start with this, evaluation word is actually number oriented. Evaluation word is not subjective. Okay, means either even if we are evaluating quality or quantity, even if we are evaluating quality, we will come to a number. Okay, that, okay, oh, this project looks 80% novel. Okay, we have to say this, otherwise there will be no comparison. Otherwise it will be like, oh, every project is novel, but we will fund these two. Why? There will be no answer to that. Okay, so now coming back to the main point, that this tool, at least, it is giving a new perspective, and it is not surface, frankly. Okay, we need to add more layers to it. Frankly, I also don't know those layers right now. Okay, but the point is that this is, in my opinion, better than the normal existing one. At least it will serve some, it will reduce some issues. Okay, right now, if you see, like many of the evaluation committees or evaluation teams, they don't consider retraction at all. Retraction should be considered. Why it should be considered? If you have not done ethically, if you have not done or published something ethically, then it should get like negative weightage. Okay, so all those things we are trying to put like under one umbrella. One another thing which I would definitely like to say about at least not in terms of our tool, let's say every student, whoever is joining, or every early career, or whoever it is, if I want to see, let's say IIT Madras Biotechnology Department, some faculty, the first thing which you will do is you go to their Google Scholar Lens. Google Scholar Lens is like that, it has that reach. Okay, so but just by looking at profile, you cannot see the quantity and quality also, frankly. Means we will just see that, okay, oh, this has this much citation and this has this much of papers and all these things. So we are trying to make that judgment easier for the viewer. Okay, that okay, now we have these many layers, now you can judge based on this also. Okay, so that is like, as I said, providing one additional layer. In my opinion, it is not harmful ideally for anyone. Okay, it is not even degrading the collaboration pattern, because people who are collaborating, they will collaborate. If I want to collaborate with you on some question, then you will not be like, okay, if you don't give me equal authorship or first the collaboration doesn't start with asking authorship or something. It starts with a question. Now if someone is contributing only 10%, ideally they should not even ask for equal authorship or something. Okay, and if they are asking, obviously I'm sure next time you will not collaborate with that person, right? So what actually we have done is, whatever is in our mind, in every person's mind, we have just tried to put under numbers. That's it. So in my opinion, it will not impact anyone, but it will give a different measure to the viewer, to the committee, to the team, anyone.
So hopefully we'll not be seeing a lot of joint first authors and joint corresponding authors after this.
So that's a good point, that it consider all those things.
Okay.
Okay. So joint authors are all given same weightage. If you have 5 joint authors, all of them will get 90% weightage.
Yeah.
There are some publication houses that ask you to declare the contribution in paper. In fact, long ago, 10-ish years ago or 15-ish years ago in my postdoc, when I published my first paper in Science Advances, you have to clearly write one paragraph who did what and how much.
Right.
To me, that was very fair, because it's like a battle. How to define the first, even if there are rules, and sometimes there is an equal contribution. People do write equal contribution, and more of so, it is a big issue in the interdisciplinary sciences.
Yeah.
So, I mean, to me, what you did is more like, reducing the inflation, the peaks, and more standardization, and then just taking all that corners out and then just making it more normal.
Okay. If I can just add one point, because you guys are here, especially the publishers, that when we ask a paper, so that is my target ideal. Okay, my Google Scholar Lens will not work without weightage. So when we went to publish this paper, because obviously we need to, that's what people do, right? So the biggest comment was that, okay, you have given weightage, but there is no support for weightage, which obviously no one can see. That, okay, so what we are doing, we are giving 100% weightage to the corresponding guy. If there are 5 corresponding, all of them will get 100% claim on all the citations. First author get 90%, second author get 50%, third author, third, fourth, fifth, sixth. All these authors, if there are 6 people in the team, they get 25%. And if there are more than 7 authors, all the co-authors get 10%. Okay, so if there is 1,000 author paper, okay, so all the co-author, in my opinion, will get 10% of the weight of citations. Okay, now my concern is how to get this number 10%, 20%, 50%. There is no way. Means this is just arbitrary number, right? So when we are asking author to while publishing that, okay, what is the contribution? Now there are these different strategies of finding contribution, that who has contributed to which section. But if you ask there a number that, okay, out of 100% contribution, or what is the contribution in terms of each author's overall, it's not, it can be cumulative, frankly. It can be cumulative is always better, or weightage wise, that, okay, corresponding author, whatever we want to give. So if that thing can be, as I mentioned earlier also, that evaluation can never become subjective. It has to be numeric. Okay, now numeric formula and algorithm and all those things we can define. That's not a problem. But we need the first part, that okay, if this is the paper, this person has contributed this much in terms of number. If that can be done from
Well, I think that will be evolved once you start
I
this
think it's
practice.
more of a framework. People need
Yeah,
to adapt it,
yeah,
right? At
yeah.
least a conversation like that is
Exactly.
out.
Yeah. So now I take this question to Veda. So nowadays we are in the area of social media, which is used to amplify the research visibility. And many times we have seen the journal impact factors, they're always showcased along with that publications. So to what extent does the impact factor influence your choice of journal and the evaluation of this scientific quality?
Okay, you're asking my personal choice. See, we are all in the same soup, so we cannot neglect the fact that impact factor has a bit of prestige, and being in the part of the system, I think we have to consider that. But if I consider when I select a journal, I think there are some more aspects to it. The first thing is, who are the audience that we are actually submitting this article for, right? Because at times high impact factor journals are not the real audience where we really want to share our work with. So it happens many a times. So so that's why impact factor is not the only criteria, but there are other, the scope, the impact, the prestige of the journal, and also the reach that the journal is giving to your particular work, because that is the visibility that you are getting through the work. So I think there are n number of factors, and also these days, because most of the journals, reputed journals, are behind the paywall, we also have to consider whether it is an open access, whether it's a hybrid or subscription. So there are n number of factors that we have to see. So that is the real life situation. And as Gaurav was mentioning, I just wanted to point on that key, as Chandra mentioned, right? Because these are now matrices, more co-corresponding authors and more first authors are actually evolving. Whether it is really contribution based, that is an ethical question that we all have to ask ourselves, right? So whether we really want that pressure on our shoulders or not. So I think that is also very important.
So when we talk about the impact factor, now my question is for Rohini, and you were also mentioning about that you will talk about the impact factor. So if publishers, they are aligned with the DORA principles, right, and they aim to move beyond this journal-based metrics, so should they take a stronger step by removing the this impact factor from their website? Would this help meaningfully improve the research integrity and also encourage the quality over the quantity? What is your views?
Yeah, that's a trick question, but of course, I'll address the last part first, and then I'll address the rest part. Research integrity. Why do we publish papers? Why do we publish research articles? Because we want to let the peers know that these are the developments in our field. Okay. Now, this could be published in a social media site as well, but we publish it in the peer-reviewed research paper. Why? Because we are publishing something which is validated by our peers. Okay, it's something reproducible, it is reliable, and it's our responsibility. Sorry. We get the money from taxpayers, research funding from the taxpayers' money. We are responsible towards them as well. And when we are conducting some research, of course, it needs to be publicized. It should be published. It should be validated, which is why we publish in peer-reviewed research papers, journals. Okay. Now, whether it is a high impact factor journal or it's a sound science journal, research integrity and ethics are at the core. These are non-negotiable. We cannot say that, okay, I'm publishing in high impact factor journal, so if the research integrity is compromised, it should be okay. No. Research integrity has to be maintained in all kinds of journals. Okay, first thing. Now coming to the impact factor. I want to tell you why impact factor was first of all proposed and what was the need for it. So this was proposed in 1960 by Eugen Garfield, not the cartoon character, the real person. So he proposed this idea of impact factor, and this was developed as a tool which will help the librarians select the journals, which journals to be purchased, okay, and which journals later to be subscribed as well. So this was a handy tool for the sake of librarians. Now this again had numbers, easy to quantify, so it became a shorthand to identify the best journals, and then it was the impact factor was connected to the prestige, as Veda mentioned. So prestigious journals will have higher impact factor, and that's how it went on. And now it became a very common practice to, put it as the evaluation criteria, that higher the journal impact factor, better is the journal research quality, and of course they should get more in the promotion, let's say promotion institution level, or even in the funding agencies when they check the grant proposals, etc., they look at the impact factor. But again, that is not the complete picture. Let's say, for example, somebody publishes some research work in the highest impact journal, okay, because it matches the journal scope and the journal standard as well. It has been validated by the readers of that journal and it gets published there. How effective it is for the community? Is it been adopted immediately, or it has got some high impact over the community? That is something again we have to think. So not every article has average citations which is matching to the impact factor of the journal. So if you consider the curve of the impact citations of the articles published in the certain impact factor journal, there is a bunch of articles or small number of articles which matches the citations close to the impact factor. The rest of the articles do not even get let's say 10 or 20 citations also. And also one point to mention, not every time the review articles fetch the highest citations. There are some other research articles as well. So again, this impact factor cannot be it is a prestige. It was perceived as a prestige, but we have to look for the complete picture here. So which is why I think when this number game started increasing and the funding agencies, the institutes started focusing more on the numbers, there came the DORA into picture. DORA is Declaration on Research Assessment, which clearly states that impact factor is not the only criteria to evaluate the impact of the research work. Okay, and publishers have signed DORA agreement. So Wiley has signed DORA, which is why you can see in all our journals on Wiley's page, we not only mention the impact factor, which is one of the metrics, journal metrics. We also talk about the acceptance rate of the journal, the turnaround time, who are the top contributors, like the top author countries, the top readers, etc. So there is a broad spectrum of metrics that we mention on our journal. So we maintain the transparency about that. Now, this is not just about journal impact, because journal impact factor is a measure of the average citations of all the articles published in that journal. When we are talking about the research impact, we have to look at the article impact as well, and which is where on every article page we have this article metrics, and it is not just about citations. So we also want to look beyond the research citations, which is why we have something called alt metric. So altmetric also considers the media presence of the article. Has it been picked up by the bloggers? Has it been picked up by some news agencies or maybe some startups, and how it is impacting the overall community beyond the laboratory research community? So these factors also matter a lot. Now coming to whether we can remove the journal impact factor, and is it going to enforce the research integrity? The clear answer is no. Because research integrity is a practice, it has to be inculcated at the laboratory level. Okay, authors have to follow it. Editors have to ensure that research integrity is being followed by the researchers, which is why we believe in transparent peer review system and transparency about the entire process as well. Publishers have to follow it, and publishers have to ensure that research integrity is followed. And of course, funding agencies also have to encourage. So, will removing the impact factor help to enforce the integrity? No. That's also because, as our fellow panelists said, that things need to be quantified. If we remove the impact factor, what will the institutes and funding agencies look for? Again, the journal prestige maybe. And now that impact factor is not there, maybe they will follow the brand. So again, we are going into some opaque evaluation criteria. So instead of removing the impact factor, what I would encourage is look at the article level metrics, create an awareness about the rest of the metrics as well, instead of just looking at the journal impact factor, and talk more about research integrity. That is going to be helpful.
Okay. So you were mentioning about the article level metrics, or maybe the metrics of metrics.
Metrics and metrics.
Yeah. So my question next to you, Diksha, that how should, I mean, in the same context, that how should the publishers like American Chemical Society, they balance the accountability with the responsibility in not reinforcing this metric-driven culture? So what are your views on that?
So that's a very interesting topic. I had been living with that like nearly 12 years now, had seen things. See, the only body that can bring some change is the funding body. And I tell you the why. People cannot make the rules that impact them negatively. Because if you really see the business aspects of, and whatever I'm saying is in a pretty individual capacity here, not necessarily representing the view of organization. When there is an economy or the system is set, right? There is a language librarian understand, there is a language everyone understand. It's easy to make a decision and get, the whole transaction done. The moment you break one part of the system, then until we have calibrated another system, we will have like a broken system. So starting from why it came in, librarian use it, then it got extrapolated, then it got, further inflated and then totally misleading to the point here. Again, saying to all these metrics are just influence and the reach indicator. Where did we confuse them with quality? That is the first thing at a PI level or the funding agency level. We really need to be very, very explicit and mindful of writing somewhere. Impact factor is just reach. Impact factor is just influence. Even alt metric. Let's say media will pick up the topic that is like in politics or, the environmental issues or the health issues or anywhere. So fundamental science published in very, very high impact factor journals don't get citation until like for decades sometimes. So wherever they are published, getting back to what can be done or how do publisher like ACS is. So I'll just give you one instance and then this will cover. Society publishers still have a lot of responsibility to have the journal. Those are driven by community, for community, by community. So at ACS, all of our editors are practicing scientists. And they come up with that lens, how does that work for people? So once I was in a board meeting of JAX. And there was this heated debate about impact factor because that journal is nearly 147 years old, right? And it publishes nearly 3,000 articles in a year. So if you just take the highly cited article, 20% or 30% of that, that would be the journal with nearly 100 impact factor. Comparing to. So this is a matrix of the total number of citation in 2 years divided by the number of article. So if you really have that maths upfront, you can really back calculate and figure out. So that is the biggest advantage of all the metrics because you can't fabricate the whole system knowing what is required to be done. So overemphasis to metrics is self-restriction. That's what one thing I would say. Second thing which is evolving now and which will help us little bit go beyond is open peer review system. Peer review should not end when the paper is published. The actual peer review should start when the paper is out. Because initially, if you really see, we publish a lot. There is a reviewer fatigue. Are reviewer really trained to review? So before even a research is out and the paper is being reviewed by some people, not everyone necessarily is able to review. There is no training like for peer reviewer. And it's a massive, massive undertaking based on the number of paper we publish. So if we really dissect the whole system into steps and see how robust those steps are, it will give us strategies to work on alternatives. So think about the post review. There you don't need any publisher or anyone for that matter. Any country can have undertaking. You have all the published paper, put up somewhere and see how the scientific community is responding to that. And that should be a very strong signal to funding agencies or the decision maker or anyone. Of course, there need to be a timeline for that, right? I mean, do we see that signal for 2 year, 3 year, 5 year? So it will give you short, medium or long-term sense of where the science fit in. Is it like applied? Is it translational? What kind of impact it has? If it is applied, is it being absorbed by industry? If it is like, fundamental, is it opening up like more questions? How many related paper came into that? So these are difficult things to do. And as a system, we try to prefer a little bit more simplistic thing, easy thing. So we are just moving into this loop of the easy thing may be still not that relevant. So we need to just break the system at some point to probably build a better system. And that probably will happen from the funding bodies and the decision maker in a particular country. Because neither the publisher nor other system will come out of it something, because it probably won't suit to like a lot of things how the system functions.
And maybe some of the institutes should take the lead.
Of course.
Yeah.
So you see the ranking thing. I mean, how does the institutional ranking is different than that?
Yeah.
So many top university in the world said, look, we are not interested in the ranking because the framework you have to evaluate me no longer. And then see, so the trap is we criticize metrics and we keep building new and we keep appreciating those metrics without understanding the consequence it is setting up for people. So here, people like us, who at least have few years in our active careers, have a responsibility to talk the things which might be uncomfortable and difficult to do, because then at least it will open conversation which people normalize these things.
Yeah, I think that's what we are trying to do today.
Absolutely.
And we were talking about the DORA. I think I'm not sure whether institutes are also having the party to DORA, if any institute wants to be part of the DORA and if it is allowed.
I think it's mainly for publisher because impact factor is.
I'm just wondering if institute declares that we are part of the DORA and we will not consider this as a matrix for our evaluation or even for hiring or recruitment.
So I think even if you declare or don't declare, you are not accountable to anyone, right? You know, it is more like your hiring committee where the decision makers say, hey, look, don't pay attention to impact factor. Then automatically you will do it in action and a lot of people will figure out, hey, publishing a lot of good paper does not get you in a faculty position. Yeah. Let's think differently.
Okay, we are coming to the last part. So I will have one more question to all our panelists. So I will start with Gaurav. Can you share one example that where you feel that current matrices or Google Scholar failed to capture the true impact and that has given you this thought process to bring the authorship also into it?
So when I started working on it, like almost 3 years back, okay, I used to do it basically based on the boasting part, okay, that many people on social media, in our general audience, in our, they always boast about it, that, okay, oh, we have an H index of this, and we have these many citations and all those things. So that was my clear, so as I said, it's not my forte. Okay, I just thought of that, okay, I have some.
So you started thinking this in IIT Hyderabad.
You can say I have been thinking about it, but yeah, the timing is kind of almost safe. So, yeah, that was the only perspective from where I came, that there should be some weightage here. Okay, and again, the weightage should not end here. Now, if you see, nowadays journals or authors are publishing so many weird kind of articles, including me, frankly. Okay, so we also publish review articles, we publish short communications, we also publish commentary, we also publish monographs, or so many different things. Okay, they also get citations. They like sharing an opinion on an open platform is getting citation. So means that weightage should also be there. Review should not get enough weightage, frankly. Review should not be, even in my opinion, means I have also published 1 or 2 reviews. They should not be considered as citations. They should be just, okay, this is this
contribution. It's more contribution.
Yeah, there is no research in that in an ideal world. Okay, so as I said, means we are trying something. I'm sure people will not like it. People are not liking it. Means you must see the debate on Twitter when this.
Yeah, obviously, when you bring down the 7,500 citation to 2,700, people will not like it.
People were like people were renaming asset index to shit index. But as I said, means I don't care. I have nothing to lose here. Okay, so. Let's see, means how it goes. The next stage is definitely we are trying to make it more independent of Google Scholar Lens and Google Scholar as such, so that people or institutes independently can use it on ORCID IDs or using DOIs and see how it can be it can become more of a better marker of evaluation. But again, as I said, evaluation, these numbers are not going anywhere. The only thing which I am very hopeful is the preprints, actually, that preprint should start getting weightage, and there should be like all this bioarchive, X archive or something like that. All of these should have like people like more of us researchers who can review. They should review directly on bioarchive, and those bioarchive comment sections should become more of a review system for the mechanism. But obviously, let's see how it will go. Frankly, journals should also open their comment sections for each paper, in my opinion. Okay. There should be an option of that. Okay, if I have some suggestion on that paper, or if I have some comment on that paper, there should be a mechanism. As I said, means I'm just hand waving here, but there should be a mechanism. In that way, the review system will become a little bit better.
Okay, so preprint, and of course Diksha talked about the post-review publication review as well, post-publication review. So I request for the next question to be very brief and precise. So whether, as an executive member of Global Young Academy, where I know as a GYA co-chair also that we have put a lot of efforts in looking into these evaluation system worldwide. In fact, last year we had published a paper from GYA in Nature about the current evaluation practices across the globe. What do you think, what is the way forward? And from the GYA perspective, can you share your thought about it?
Yeah. So the question itself is very nostalgic because I got elected in the same auditorium as the executive member when we did the GYA AGM under Chandra's leadership last year. So when we have all these coffee chat interactions, like ask our friends like how the evaluation practice happen across the world. So what we understand is it's always a balance between traditional evaluation to responsible evaluation. So every country is at some point of time in some at some part like they are still practicing traditional evaluation to an extent, but they are definitely in the journey towards responsible evaluation. So as mentioned about DORA and CORA, so all these aspects are now being part of this evaluation. So it is getting more responsible. Now people are understanding the value of impact. And not only the national impact, the global impact, how your research reach, length and breadth and so on. So I think it is improving. And I think that Hong Kong summit, they mentioned that they also added the integrity aspect that you mentioned, that should also be a very important aspect into it. And in UK, they also started a very important aspect of like this excellence. Because in the early stage, I think we are more because what I see over different verticals like CSIR, ICR, ICMR, I don't know how the number metrics of, for example, publishing 12 publications is different from a 15. How you can differentiate the quality of a scientist or a research just based on these mere numbers. So I think this pressure of publication or publish or perish, it is getting quite removed over the time. I think that's a good thing because now we can more focus on excellent research and focused research, which we are really attracted to or interested in. And I think that kind of an impact is happening all over the world. I think we can also learn and imbibe into our system. Yeah.
Thank you. So Rohini, very quickly, you talked about the general impact factors. So do you think that researchers from the well-resourced institutions, they have an advantage in assessing the journals, and that basically perpetuate this, finally, the inequities in the knowledge production, evaluation, and of course, the reward system? Yeah.
I'll be very honest. Yes. I mean, the institutes which have got more access to this and having a good infrastructure, the research quality, the publication quality is definitely better. And of course, the evaluation system that they have is stringent. So there is a competitive nature nurtured in this well-accessed and well-equipped institutes. But recently, I have seen very good change. India level and of course at the global level as well, wherein researchers from college levels are publishing very good articles, and it is not just about high impact articles, but they are publishing patents, they are transferring the technologies, which is a good good progress that I can see. And the way India has done remarkable growth in the publication from decade 2013 to 2023. India's publication growth has increased by 184%, the highest across the globe, and we are the third largest contributor of research publication in science and engineering. And this is the data published by National Science Foundation, and it's for the all publishers. So we are doing good growth. And inequities, of course, we are trying to deal with it. One nation, one subscription is one of the best movement, I would say, that wherein they are the government has involved all the colleges, government funded institutes and colleges, etc. And the way private institutes are also doing excellent in terms of publication, in terms of awareness about the quality over the quantity. The program like Spark, of course, where the internationalization of the research collaboration, these all things are definitely helping remove that inequities, I would say. And can I just take one moment?
Yeah.
So I just wanted to mention about few things that when there is a more attention to the popular research topics and maybe the Diksha mentioned about the popular topics or the topics which are favorite of the policymakers or funding agencies are they are picked up more, and they gain more attention on the social media. That's where the responsibility of the publishers and the editors come into picture. We as the editors always look at the fundamental research as well. So there are highly cited articles. At the same time, editors pick up the articles which are practiced by a smaller community, but they still have a greater impact. And we do feature them as editor's choice or hot topic, or even we highlight the young researchers through our various features like Rising Stars or Women in Material Science. So as I said, it's when it comes to the better science, it's the contribution by everyone, the authors, the publishers, and of course funding agencies and policymakers as well.
Thank you. So yeah, I think my last question to Diksha. So if you need to redesign this research evaluation, or maybe in your organization especially, what will be the first principle you would discard?
So I will be very explicit at the entry point itself. Just have a high level classification of which segment you are operating in. I think 60-70% of our problem will be solved. Because if you are evaluating translation, you have a product out. If you are evaluating applied, you may have patents and problem solution fit. And if it is fundamental anyway, you can easily know wherever it is being published. So defining that research, even Chandra, this can nicely translate into the faculty recruitment as well. What is the purpose? Because you can't hire a fundamental person and say, now you set up a startup, which most of the time issue happens because how the expectation and the priority of institutes evolve. So that is one thing. Second thing, we should not believe everything that we count matters, and everything that we cannot count does not matter. So since we can do something is not the only thing, and we should be really aware of that. What we can measure is the ability, but that may be misleading.
Yeah. Thank you. I think we are running at least half an hour late. So I will open this panel for any question, maybe one or two questions we can take. Any questions? Yeah, Anil. Mike. Yeah. Be precise, and I request the panelists also to be precise equally for their response. Yeah.
Yeah. Thank you for discussion. I will come to the questions. Like we have the panelists like Vile and ACS, particularly the publication sites. At the other sides we are researchers. But in the one first way, like why we need a publisher actually? We don't need a publisher. Let me finish. Because democracy is the best way to evaluate any system actually. And that is the power of our nation. Same thing like if I publish, I'm giving a royalty to you, I'm giving the money to you, everything to you. And but at the returns, I'm struggling for my life, for getting a jobs. Then you are looting from the academicians and all these things. It's better to keep like Amazon. My paper, I'll put in Amazon. If somebody like it, he will buy it and he will give the money to me. Why I need a publisher in between? These things actually I didn't understand till now. Thank you.
Okay. Hopefully we will understand it today. Yeah.
This is absolutely a valid question.
Yes,
And I
absolutely.
was asking this question more as the emerge of AI. So look, the question you are asking is this the access to information or is this access to credible information? No, you actually cannot. And I tell you the reason why. Just give me 2 minutes to explain that. When we use the word peer reviewed, like I found out something, right? And I believe I have done ethically nice, great, perfect. How would a person sitting in other part of the world know you are a nice man and believe everything you are saying? Science is not commodity. If a new science comes, that's a wrong footing we are having a discussion. So the discussion here is not the information access. Understand between the two part. It's the credible peer reviewed information. That's a separate question. Do we need peer reviewed information or not? If we don't need peer reviewed information, then your point is valid. We don't need any publisher or any guarantor in between. But this is really the point of publisher provide that stamp saying we guarantee the information here is credible, trustworthy, and had been checked thoroughly.
And gets
This is the value add.
and gets the copyright of your work.
Whatever, yeah. This is these are. See, so this is the difference between peer-reviewed information and information. So now on any generative AI, you can get every information, but who is there to guarantee whatever generative AI has said is right? Though most of the time it is right. That is what that guarantee. Like it is exactly like a reference letter in some sense.
What? If I can add one point here, means actually I like with what you are saying, okay? But I will try to modify your question to some extent. That okay, let's say even if you are paying to the journal, there should be a mechanism, frankly, that okay, based on citation, based on some perspective, you also get something out of it. That I agree completely. Okay, means because see, ideally you have put a product online, you are not getting anything. Okay, let's say a job, you get it based on that. That's a different perspective. But in an ideal world, okay, there should be some mechanism that, okay, if you are paying, if you are not paying, if you are putting it in a subscription mode, then let it be that, okay, you don't get anything because you have not paid. But the point is, and this is, I'm saying in a perfect world, okay, that, you have paid $2,000. Now, depending on if it get like 2,000 citations or 5,000 citations in a over a period of 5 years, you get some royalty from it. That okay, $100 per 2,000 citations you will get. I'm just saying, okay, there should be a mechanism like that, okay, because ideally authors are getting zero, okay. I'm not saying that publishers are wrong here. Publishers are also, see, either whatever it is, it's a business, right? But if it can consider a little bit about authors, I'm sure it will be.
I think we are a little deviating from the topic because
Just one point here. You have two pieces of paper written with you. The one plain file with no logo, no brand. The another file which says from this publisher published in this. Which one you trust you more? That's it. You think about.
Yeah. Anyway, I think we are deviating from the topic, which is not. And anyway, in the interest of time, I think we will close this panel here. Sorry, Manohar. I know this is a very hot topic, and we can go for the discussion and continue. So let me thank the panelists for very candid discussion. Sometimes the questions are a little uncomfortable, but yeah, I think that's what we wanted to have it. So let me thank all the panelists for their time, and we will take a very brief break for 10 minutes for going for the next technical session. Now you have earned it. It's not. Yeah, absolutely. Yeah, thank you, Gaurav.
there is information pollution. We are looking for a credible information.
Exactly.
Not,
अभी AI क्या निकला तो और problem.
Next have a group. You can take.
I will hold it.
Yeah. Hold it. Chandra, we are with you. That is
on from polymer to carbon sits at a fascinating intersection of materials science, functionalities and applications, spanning various domains of energy storage and beyond. We have an exciting lineup of 4 distinguished speakers in this session, each bringing unique perspectives and insights into this evolving field. Let me remind you that each session will have 20 minutes and there will not be any Q&A session following the session. So let me please call upon Dr. Vinayak Kamble from School of Physics, ISER Thiruvananthapuram. His research areas include nanostructures and thin films, surfaces and interfaces, defect-induced transport properties of materials, dilute magnetic semiconductors, thermoelectric materials, and solid-state gas sensors. Sir, please.
Thank you so much. Yeah, it's a pretty broad spectrum that he described, and it is the spectrum that I am trying to justify here. Okay, a very good afternoon, everyone. My name is Vinayak, and I know that the audience here is also pretty broad from various backgrounds, so I've tried to keep it engaging for everyone. What I'm going to talk today is, I know there's a lot of, primarily many people work in the batteries here, but by and large, many people are from electronics, some are from other backgrounds and things like that. I will try to engage everyone at different points in this case. What I'm going to talk about is where we started this journey as a serendipity, and what that serendipity led to a series of 5 publications and the story of that into a nutshell, and putting it into a larger perspective of how artificially engineered materials can make a new advancement into the field, which can at the same time, being from physics department, we are interested in knowing the mechanisms and nitty-gritties, and there will also be some sort of an output which we'll try to bring in. Okay, so to begin with, that's kind of my lab. We call ourselves Smart Lab. It's a sensors, microsystems, and renewable technologies lab. Our main business, as he pointed out, is semiconductor devices for chemical sensors and so absorbers and thermoelectrics and energy harvesting. So essentially, all of this would have some interface later. And where do I belong is this tip here. Of the Indian peninsula, where you can call everything in India is North India. And this is where we are in Trivandrum. You are most welcome to come to our campus, even for your holidays. And it's no less than a holiday resort, for that matter. So we are into the foothills of Ponmudi Peak. What I would like to start with is a materials perspective on the onto this audience. Is the man has made a significant advancement, and this is probably where we are right now into this silicon age. And silicon age, or maybe you can say plastic age or carbon age, or whichever age you want to, but it's a synthetic age, which are man-made stuffs, right, which did not naturally exist. And the man-made onset started much earlier when we started alloying things, and today we are into much more complex things. So how did it go? It went into through many series of discoveries and innovations. And what do you mean by discovery? Is where you kind of find something is magnetic, it attracts with a certain force of attraction, maybe it's a discovery, right? But then when you use those magnetic things to create magnetic random access memories, it is an innovation, right? So the discoveries are something which drive innovation, and innovations also have breakthroughs when there are breakthrough discoveries, right? So a giant leap comes only when there is a new discovery which is happening into the field, and that's how things move ahead. Also, to talk about, similarly, there was, I don't know how many of you have seen this paper, where the title is very interesting, and they actually justify their title by taking a bird
poop and putting it onto graphene and then making a composite and showing that yes, it also kind of helps in electrochemical activities and things like that. So man started making things, but to what extent are we going, and what is our intrinsic drive in doing so? Okay, so what I am going to show you is basically, as my title says, is electron phonon coupling in oxides, which is leading to thermoelectric properties. It's a series of this 4 papers where we actually went into, and I'll come back. I've made this comparison for which I'll come back. And where does it actually have applications? Applications are immense, where there are lots of heat getting wasted into the surrounding. It is happening in your electronic devices, it is happening in your automobiles, it is happening in every industrial process. Not everything is 100% efficient. A large fraction of energy is actually dissipated as heat. So can you also tap that potential and generate something and make it useful for working devices? So thermoelectrics basically comes into that class of material. Very quick summary of last 1 century. Somebody in 1800 or something, where Seebeck, he discovered this phenomena that if I take a piece of a sample metal and I have a temperature gradient, it will generate an open circuit voltage. Right? But this degree of open circuit voltage differs from materials to materials, so it must be an intrinsic property of the material to generate different values of Seebeck coefficients or Seebeck voltages. Essentially, later people saw that, like a solar cell which also generates open circuit voltage under light illumination, this can also be tapped as a power generation source, and the efficiency of power generation is limited by the material properties. Now there are range of applications where it can be used into renewable energy spectrum, starting from automotives to even healthcare wearable devices, which we will see some glimpses later, and so on. So the times, what makes more important about these things are whether it is metallic, insulating or semiconducting, and within that we need a sweet spot where this thermoelectric power generation efficiency maximizes. Now this is not irrespective of the lattice structure, because the lattice structure is which has lattice vibrations, which is what interacting with these electrons, the number of electron density which I have plotted it, and that interaction between the electrons and the lattice vibrations is something which is kind of limiting your applications. What kind of materials have people been using? You may get, even like somebody said, Amazon. You can go to Amazon and find a Peltier module. It is made up of bismuth telluride. Bismuth telluride is the state of the art material. People have also shown state of the art efficiencies in lead tellurides and things like that. But as you know, tellurides are toxic and they are absolutely less earth abundant, so the cost is much higher, and higher than what? Higher than most other oxide or silicon or such kind of materials. You can see this is a nice paper in small structures, where actually they have summarized a lot of materials and their temperature dependence of thermoelectric power generation efficiencies. And what you can see is, in this region of temperature where there is very high temperature range, there's hardly anybody here. And who exist in this temperature range is either silicon germanium alloys or oxides, which are very, very stable at high temperatures, and they generate a lot of power things. So what gives me a better edge for oxide is their chemical stability and the ability to control their functionalization by controlling the oxide. Those who have worked with oxides here, I'm sure oxides is their first love, because they will know how much tunability do they offer as a function of their chemical composition, morphology and things like that. It is just incomparable with any other material. Now, so what we can see is that oxides definitely have a room where they can do this, but the problem with oxides technically was that extremely ionic characters in most oxide, because oxygen being most electronegative element, and that makes it ionic, which gives you large band gaps. Large band gap means very low carrier concentrations. The other problems with most of these materials is that very high lattice thermal conductivity. So once you are trying to maintain a temperature gradient across a sample, high thermal conductivities can immediately work like a heat shot, and it will reduce your efficiencies. So first and foremost, I want to decouple this heat flow and I want to still have a good electrical conductor. Like you can imagine having a silver spoon, which is a good electrical conductor as well as good thermal conductor, right? But I cannot have something which is good electrical conductor but a bad thermal conductor. Okay, these are limited by the nature's law, which is called Wiedemann-Franz law. Wiedemann-Franz law, they identified it, that electrical and thermal conductivity have a correlations. What we showed in this paper here, which came in 2021, approximately 5 years now, but I still celebrate this, 80 citations over 5 years, very revered in review papers, because what we showed in here, you can break down this correlation between electrical conductivity and the thermal conductivity by making some sort of a heterostructure which is carefully engineered. So how this serendipity happened is that we were only looking at zinc oxide, and to get high densities we were actually hot pressing them under graphite dies. And what that student found is that even whenever he is doing Raman, he is getting graphite signature even in zinc oxide pellet, right? We broke it up to a certain depth, still there is weak and weak Raman signature, which means graphite was diffusing inside when you are hot pressing it, when you are pelletizing it at high temperature. And that sort of gave some reducing atmosphere, as well as it improved the electrical conductivity tremendously. And you can imagine zinc oxide, which is normally an insulator of 3 electron volt band gap, the electrical conductivity, if I have that plot here, this is pure ZNO. This is what he got as a zinc oxide graphene sandwich. Like you can imagine graphite being diffused from the top and bottom. In between you have more or less pure ZNO. So it is not only working like an electrode, but it is acting like a shot. And then we decided why not to coat each particle of ZNO with graphene, right? And in that case, can it actually work like something which bridges the two grains? And you can see here the order of conductivity that is a jump from 10 power minus 8 to all the way 10 power minus 1. 9 orders of magnitude jump in the electrical conductivity. It is huge. Okay, and why does that happen? That is what we started probing backwards in the other way. And you can imagine it is not only that it is pure graphite equivalent conductivity, but graphite shows you metallic character. This is insulating character. So it retains its insulating character, still gives you the electrical conductivity as good as a metal. Okay, so these things were very surprising results. And then we started looking at it. We started doing even on the individual particle, when we did this scanning tunneling spectroscopy, which basically tells you the density of states, that for a zinc oxide the band gap is large, of the order of 3 electron volt, but for graphene or graphene oxide coated materials the band gap is hardly 0.5. So it is on the surface it is working like a reduced graphene oxide, but interior is something else, and that is something which gave in. So this is a kind of process flow. You prepare the particles, you dope it with something, because still the native conductivity was not enough. We had to dope in aluminium to make more defects and more carrier concentration, and led to centering in spark plasma centering, and then characterization and measurements. And what you can see here is that the difference, sorry for this poor resolution, what you can see here is that when you do this scanning tunneling spectroscopy, a large tunneling current is seen just because of this graphene encapsulation. And because of that, we could also see that the effective band gap of the system was also reduced, and not just that, it increased the mobility of the material substantially, which led to final this thing. So I can summarize the results into this, for example. So you take 2 zinc oxide particles, put them next to each other, right? What happens is, on the surface, because of your oxygen, the oxygen traps some of the electrons. There is a surface band bending. This band bending limits electron going from one particle to the other. So it's like an energy barrier at the surface. Now what we saw when the graphene was incorporated, graphene locally made chemical bonds with this, satisfied all those oxygen vacancies which were there onto the surface, and it kind of bridged the gap between the two materials and gave a low conductivity grain boundary, high conductivity grain boundaries, which gave me not complete reduction of the band gap, but it gave me a very partial reduction of the barrier at the surface, which leads to a process which we call it as energy filtering, because only high energy electrons can pass and low energy electrons cannot. So that energy filtering happened. Now what happens to the heat, you may ask me? Will graphene also work like a heat conductor at the interfaces? And it does not, because the heat does not work like that. It is not, heat is carried by the electrons as well as heat is carried by the lattice vibrations. Now the lattice vibrations are very, very sensitive to what these lattices are made up of, right? Their masses, their effective ratios of contrast in the mass, in the chemical compositions and things like that. So what we saw is that if the thermal conductivity is measured, the thermal conductivity of the composite was very, very low, because the periodicity of the lattice was broken at the grain boundary, and a foreign atom was introduced like carbon, which had a very different natural frequency of vibration unlike ZNO. So the phonons are not able to propagate from one particle to the other particle, and it leads to a effective phonon scattering, and that phonon scattering you can see as a reduction from 35 to all the way something close to 5 watt per meter square. And we tried to identify what could be the reasons by modeling these thermal conductivities, and what we see is that the grain boundary contribution, which is simply like, you can imagine a phonon is traveling there and getting reflected from the wall. Okay, so that is the grain boundary or the boundary scattering, what we call it as, which was very dominant in this case. And we then asked a question, okay, if it does with ZNO, how about if I start with indium tin oxide, which itself is very conducting oxide, right? ITOs, I'm sure many of you are using ITO electrodes in your solar cells or batteries or wherever devices you are working with. The problem there is very different, because ITO itself is heavily degenerately doped with tin. Indium oxide is degenerately doped with tin, so the defect scattering is quite high. But the problem is of the density there. If you make ITO which is of low density, you might actually get low thermal conductivity, but you compromise on the mechanical aspects of it. And then we saw that yes, densifying but with graphene oxide made it much better. The other problem, okay, maybe it works with only a certain range of oxides with certain conductivity. Does it also work from graphene oxide to graphite? When you do that, we tried answering this question by including graphite into ZNO, but lot of things, various different things were happening at the grain boundaries which were acting like a parallel resistance, and that did not give you exemplary performance like the other ones. So that is what I would compare this finally into this table, that the hybrid where the particles were coated with graphene were actually much better engineered materials optimized for all of this, whereas a more crude composite of either aluminum zinc oxide with graphite or ITO with graphene gave me much low performance, but nevertheless it is comparable when you normalize with the cost of tellurides. Tellurides are heavily costly and toxic. You can work with the same larger amount of material in the same cost and produce the same amount of energy. So in that case it is very sustainable and economical. And finally, where is this thermoelectrics going right now? It is going on into all of your wearable devices, because your body carries a lot of heat and the surrounding is actually cold. So from that temperature gradient you can actually generate few millivolts, and that is good enough to power your sensors and things like that, whatever wearable devices you are going to wear and things. It can go into secondary power sources for various things. These are wearable devices. It's a very nice review for if people want to get into. It's in micro thermoelectrics and natures. So now what we are also trying to do is, my other business is in chemical sensors, trying to incorporate onboard power generations with thermoelectric devices for wearable devices and things like that. A lot of things have been achieved, a lot of things have to be achieved in terms of device prototypes and getting into the directions. And with that I will stop here, and the organizers don't want me to be questioned, so I'm spared. Right. They said absolutely I can say anything and get away here. Right. So I would like to thank formally, first of all, ANRF, ICRB for the funding which we received for conducting this research, my institute, my collaborators, my students, and of course my family for the support. Thank you so much. This is one quick video of this wearable power generation from RF energy harvesting thermoelectric device. You can see when we turn on the RF source, walkie-talkie, it generates about a few millivolts of voltage, and we are getting about 1 microamp current for, I'm sure the ladies sitting here will appreciate it much more. We can work with wearable devices with these things. Yeah, thank you so much. Yes.
Thank you very much, Dr. Kamble. And I request audience to please note down your questions and catch hold of our speakers during lunch hours.
If they could find me.
Thank you very much. It was really insightful talk. Now may I please call upon Dr. Sonu Gandhi from National Institute of Animal Biology, NIAB, Hyderabad. Her research areas include intersection of biosensing, nanotechnology, diagnostics, and sustainable materials. Ma'am, please.
And congratulations for the 15th anniversary. I was on the 14th anniversary as well here. So yeah, so this is my second year basically officially. So I will be touching upon a bit on the pesticides. Though our lab works on various aspects of pesticides, toxins, antibiotics, and also scaffolds for tissue engineering or bacterial and viral diseases. This is the work of Sagar Narlavar in our lab. So he works on the monocrotophos pesticide, which has been categorized as a hazardous pesticide, and we know that it is a neurotoxic and ACHE inhibitor, and it has been classified as the class 1B pesticide, and there is the acceptable daily intake limit is there, and we know how it is spread. Usually farmers are not well educated and they spray the pesticides on the crops without any measurable concentrations, and then it percolates into the crops and soil and water, and also traces of monocrotophos has been reported in the various animal and animal byproducts. So this is hazardous to human health as well. There are various reports have been reported for the monocrotophos toxicity, and the biosensing platforms are available, which is conventional and time consuming. Here the biosensor plays a pivotal role, and here is the unit of biosensor, how it works, which I think no need to explain, as we all know. So this is the initial work which he has ignited in the lab. This is based on the best out of waste approach. So the plasmid isolation columns which we use for the DNA or plasmid isolation, which we usually throw after the use. So what he has done before, he was using the partition selects process, in which use the aptamers from the ssDNA library to find out the high affinity aptamers for the monocrotophos. So what he was doing, he was using the nanomaterial as a graphene nanoplatelets or the graphene oxide, and mixing this ssDNA library with the target, which is our monocrotophos over here. After incubation, he was doing the centrifuge. So you can see the supernatant was not clear, and hence the material was present in the supernatant. So what he has done, he made this the partition selects cartridge column, where he has just washed it, cleaned it properly, this plasmid waste columns, and packed it with the GRNP or GO material, and incubated the ssDNA library with the monocrotophos, and then just centrifuge for 1 minute, and the flow through was collected, and after PCR we could see the single band. This way we could reduce the select cycles, because for the small molecules select process usually takes 35 to 40 rounds. By using this process we have reduced it to 17, 18 or 20 rounds max. So this has saved our lot of resources and time. So with this material, what he has done in this Go selects all the characterizations. He has compared with the Go as a standard material and GRNP as the test material, and various characterization with the SAM, with the Bayer and the ssDNA incubated material with the EDEX analysis was performed for both materials, followed by the XPS analysis for the elemental composition, where you can see in the presence of ssDNA, nitrogen and phosphorus peaks were there in both cases. Further zeta potential measurements were done to confirm the change or the adsorption of the DNA onto the surface of the material. Later on, the select rounds were performed. You can see that we could do only up to 17 rounds, which gave us very promising results together with the negative selection in between for both the material. And this is the selection rounds gel, which could give, you can see it's a single band in all the processes. Further cloning and sequencing gave us the 8 unique sequences in the case of Go, and 10 unique sequences in the case of GRNP. To understand the aptamers affinity, we have to do the aggregation assay. For that, we have synthesized the in-house nanomaterial, which is gold nanoparticles, and it was characterized by the DLS, zeta, TEM, and after aggregation with the particles. Further, salt concentration was optimized, and aptamer concentration was also optimized. With this, the 8 and 10 unique sequences were thrown upon the aggregation assay, where one of the aptamer, which is MPGO130 and 999 in case of MPGR series, were selected and thoroughly characterized by the UV visible spectroscopy, and the KD value was calculated, which is the prime importance to understand the affinity of the aptamers. Later, these aptamers were tested for the cross-reactivity with the other closely related pesticides in both the cases, and we would also like to understand the secondary structure of these aptamers. So, one of the aptamer gave us the parallel G quadruplex and the random coil in the case of MPGR 999. In silico analysis, we have also done to understand where these monocrotophores exactly fitting into the pocket of these aptamers. Later came the idea of fabrication for the biosensing platforms, where we have used the SPC electrode. So this is the Bayer electrode with the SPC, and this is the aptamer coated electrodes. So you could see some kind of depositions, and the EDEX analysis were also done. So nitrogen and phosphorus was present from the aptamers. Contact angle gave us the decrease in the contact angle, so which shows it is hydrophilic in nature. So then we have fabricated the sensor and characterized for its optimum performance with the scan rate, pH, and the aptamer concentration, and then final testing at different concentration with both the aptamers, where the LOD was 0.58 and 0.78 in both the cases. And later, the real sample were also tested, like tomato lake and soil and etc. Stability was also tested, and it was validated by the HPLC in both the cases, which was in correlation with the RST range. Another concept is on the best of waste approach, as we use the toner cartridge from the lab in the offices, and then after use we usually trash it. So what he has done, he has utilized this trashed cartridge, and because it has the carbon in it and it has the iron also in it, which we came to know after the EDEX analysis. So this is the kind of a principle which he has utilized in the SELEX process. So here is the SELEX DNA library, which was incubated with the monocrotophos. Then the carbon black material was introduced, where it will absorb the non-specific aptamers DNA library, and then you bring the magnet close to it, and it immediately will partition the specific bound monocrotophos with the ssDNA and the non-bound ones. So this is the carbon black, which looked like in its native state, and then we oxidized it, so it is soluble. So this is the kind of a video you can see. It's he has dissolved it. it's not dissolving when it is a CB format. When we have oxidized it, it is dissolving immediately. So when you bring a magnet close to it, it will really pull all the material immediately. So it's a very efficient partition method which he has again developed. This material was further characterized by the SAM. So the CB and the OCB material, you can see it's kind of a particulate matter, and then after incubation with the ssDNA and the EDEX analysis and the TEM and HRTEM SAED pattern also correlate with the amorphous structure with the proper 0.24 nanometer D spacing. XRD also we have done to understand the nature of this material. So it was showing the graphitic plane and fractions and the elemental composition in the XPS, where you can see there is the increase in the iron content when we have oxidized it. Further, we have also characterized by the FTIR and VSM to understand its magnetic properties. Then we would like to understand whether this ssDNA adsorption, how much OCB is required in this process. So different concentration of the OCB material was used from 2 to 10 milligrams and characterized by the UV spectroscopy. So you can see at 10 milligrams, 95% of the material is adsorbed, which was again we have corroborated with the native page. So you can see there is no band, which means all the DNA material is adsorbed onto the OCB. Then selects rounds were performed up to 16 rounds, and hence we got the 13 unique sequences. These sequences were then tested through the aggregation assay, where MPCB 333 gave us very promising result. Then we have done the CD spectroscopy, and the KD value was 61 micromolar, which was quite high, and we were not very convinced with. So we would like to go ahead after the testing for the cross reactivity. It showed that it is specific for monocrotophos. Then in silico analysis was also performed, and in the CD spectra it showed the parallel G quadruplex structure. So to improve the KD, what we have done, we have truncated this aptamer at different sites. So this way we have generated 8 unique sequences in which MPCB 333D gave us very promising results. So this was further characterized, and you can see the KD value was 27 micromolar in this case. Further, we would like to tweak more. So what we have done, the point mutations in these aptamers, but we could not get many promising result. Then we would also like to confirm that this the DNA displacement is happening because of the interaction of this aptamer with the monocrotophos. So what we have done, the DNA strand displacement assay, where we have used the FAM labeled and the BHQ1 probe. So what it does, when it interacts the FAM labeled probe with the quencher and the monocrotophos comes in the soup, then this FAM labeled aptamer will bind with the monocrotophos, and you will observe the fluorescence. So in this case, the KD value was 8.46 micromolars, and in the truncated one it was 3 micromolar. So we were quite satisfied with this kind of experiment. Then different concentration of these both aptamers gave us the LOD of 0.72 and 0.61, and the cross reactivity we have also done together with the mixture of all the pesticides. So you could see that it is binding with the monocrotophos, and also we could see good RFU in case of real samples. Then it was validated by the HPLC together with the fluorescence sensor. This is the sensor which he has developed for the AACHE. This is enzyme based. So basically he made a hybrid material, AU and W, WS2 nanosheets. So this is based on the electrochemical setup. So he has used AU and W, which is gold nanowires, and this is the WS2 nanosheets. So then this was characterized to understand its elemental composition, morphology, and the different combination of these ratios were prepared from nanocomposite A to D, which was further characterized by the EDEX and the Raman to understand its 2H phase of the WS2, which is very important to maintain its conductivity. Then it was characterized by the CVDPV, SWV, LSV, and EIS, and scanning parameters were also tested in this case based on the scan rate, by all the 4 parameters, and the HR time analysis of the individual components together with the hybrid was carried out by the HR time, SAED and FFT spectra, which was in correlation with the 0.23 nanometers of d-spacing in case of gold nanowires and 0.27 nanometers of d-spacing in 100 plane for WS2, and this hybrid zone shows the AU and W zone, and this is the WS2 zone. So when you combine, you see both the patterns in case of FFT and SAD spectra. And later we have done XRD to understand the composition of the individual material and the composite, and together with the HRXPS analysis, which were corroborating. And AFM analysis gave us the difference in the height profile of this material. Then we fabricated the sensor using the SPC electrode. You could see this is the bare SPC together with the EDEX with single carbon peak and the nanocomposite D. You could see the wires and sheets-like structures in the EDEX spectra. It's quite clear. And the enzyme immobilization, you could see kind of a deposition. And the sensor become more hydrophilic when you treat it with from the bare to the nanocomposite together with the enzyme. Later optimizations were carried out via various electrochemical parameters by the DPV, LSV and WSV for the scan rate, pH, temperature and other parameters. Different concentrations were tested for its analytical performance. So in case of DPV, the LOD was 48 femtograms. For SWV, it was 87 femtograms, and for LSV, it was 84. And we have also tested the stability up to 28 days. So these samples were also tested in the real sample for this sensor as well for the HPLC. So it was in the range together with the sensor. We have also made the antibody-based sensor for the monocrotophos detection. Here is the molecule which were chemically functionalized and conjugated with the carrier protein BSA and characterized by the TLC, FTIR spectra. And gel was done, native gel was done to understand which molar ratio we have to take forward for the antibody generation. So with clarity, it was 1:100, which was giving us the red shift and the decrease in the fluorescence intensity. Then we raised the antibodies and tested the binding efficiency of these antibodies. The graphene oxide was used as a nanomaterial to fabricate the sensor, which was then characterized by the zeta and XPS EDAX analysis. The sensor was optimized for its best performance, and in this case the LOD was 0.49 picomolar, and we have tested the cross reactivity in buffer pond water vegetable extract and the stability up to 21 days. This is again the best out of waste approach which he has used, which is known as the chroma grid. So here you use this kind of a waste PVC sheets and the ring like structures which you usually throw. So he has sticked it onto the PVC sheets and used the material which is known as the chromogenic reagent mix with the alcohol. So it gives you the color when you put the monocrotophos into it. So when there is no monocrotophos, dark color will be there, and when the concentration will increase, the color will kind of a decrease. So we have used 3 substrate in this case to understand which substrate is best for us to differentiate in terms of visual detection. So indoxyl acetate, DTNB and alpha-NAC assay were done in this case, and all the parameters were calculated by the colorimetric app and the spectrophotometer, color graph app. All the applications we could use in all the 3 assays. In this case, DTNB, the LOD was 0.562 with the colorimetric app 0.493. So spectrophotometer 1.3. So like that, you see there is a difference in the LOD or LOQ depending on the app and the kind of instrument you use. So you can choose based on your application and the field applicability if you want to go for the point of care device. Then he has tested this chroma grid with 13 real samples and compared it with both the assays, and we were able to detect it. And this is the LOD LOQ with all the 3 assays. And then the summary of the work done that he has developed various sensors, and LOD and LOQ were compared. And with this, I would like to thank my lab mates. This is Sagar, who has done all the work, all the funding agencies, and yes, thank you.
Dr. Gandhi. The work truly depicted the importance of interdisciplinary research in today's times. And now may I please call upon Dr. Nandimalla Vishnu from Geetham University, Hyderabad. His research include interdisciplinary areas of material science, biology, physical and analytical chemistry, while designing low-cost point-of-care devices for human well-being.
And myself, sorry. So myself, Dr. Vishnu, I'm currently working as an assistant professor in Department of Chemistry, School of Sciences, Geetham deemed to be University. And thank you, sir, for inviting me as a speaker for this particular session. Why? Because the theme itself says that from polymer to carbon, which are giving a pathways to the functional nanostructures. Why? Because which is very nostalgic to me and also closely associated to me. As a PhD scholar, I initially started with one of the monomer, that is aniline. So in the 2013, and that gave me a really nostalgic feel. But whereas coming to the theme, so I just restrict myself to keep into one vertical, like where here I just would like to express only and also my research findings on the carbon and polymer functional nanostructures. Under that category, so I used two basic carbon materials, like one is carbon nanotube and also pencil LEDs, like which are replacing the conventional electrodes, like which are available, and to make a cost-effective approach. So in this, of course, we are aware carbon nanotube is exclusively used in various sort of things, and also not only limited, but in the last completely one day, like we had discussed about carbon storage and everything. Of course, today, like I was pretty happy to listen many of the voices, like about saying about the sensors, and under that category, I also belong to that category. So I was very happy that in my case, like in the initial stages, like what we done is like we took the carbon material and we also added this aniline or its derivative, and also under the electropolymerization, we tried to make a composite mixture like CNT slash like polyaniline or polynaphthylamine. So those are the two monomers I try to use and synthesize electrochemically by electropolymerization. So actually this is a process like where we can able to convert the monomers to polymers, and also like we can able to convert various organic compounds into value addition products. So during my era, like what we done is like this was the problem. I was trying to see my peers, I mean like my I joined a PhD group, like whereas like they said that till now like we didn't explode in this particular area and we failed. So at that point of time I started to work on CNT, and that is the only carbon available in my PhD lab. And then what we done is like I just took the aniline and I just tried to dissolve in the ethanol, and I try to add that into the PH7B phosphate buff solution, and later on I just subjected for electropolymerization, and I found that there is a formation of polyaniline in pH7 conditions also, which is entirely different. At that point of time I'm not aware like what exactly happened and everything, but later on stages we found that, and we compared it like whether is it really a polyaniline formed in pH7 PBS conditions or neutral pH conditions, which is entirely different. So here I can say the complete credit goes to the what is this carbon nanotube, and also like what is this like the potential like which we really applied during the span of time. And whereas we also compare like what is the novelty over here. Yes, obviously the pH2, which is very conventional and very regular practice, like how they used to synthesize in on the matrix, and also they used to explore it for various applications in electrochemical storage and all those stuff. But whereas here, like what is the added advantage over this particular platform spectrum is like here we can able to reduce the background noise, which is very crucial without compromising in the features of this amine and all those groups. Like, so I just started to work on this particular task, and also as a model analyte we also try to explore it for the ascorbic acid sensing, and where we found out it is one of the interesting thing, and we compared, like of course finding is very quite simple, but again, like to narrate a story around that is like really competitive and also like very difficult. So at that point of time, like I started to discuss review meetings with my faculty. So he just said that, like, first of all, you just submit the samples to the characterization, and later on I found that, like, okay, carbon nanotube, like the outer diameter is only the thing like where we see the enhancement, so such that we found that, like, okay, the carbon nanotube outer structure is behaving as a very good platform for the polymerization, and also unaltered diameter is provided inside the carbon nanotube, indicating that the outside of the matrix is like really curious and also like helpful for the polymerization in the specific conditions. And later we also found that, like, we subjected for the Raman studies, and we found that the enhancement in the graphite peak, this is the G band, which is corresponding, saying that, like, the polymer which is formed in the pH 7 conditions have shown a significant enormous increase in the sp2 carbon, indicating that you might be able to witness the benzenoid units, like, which is a part of the polymer. And again we compared with polyanyl, which is synthesis in acidic conditions and basic conditions, found that, like, we see both the polymer patterns are same, like without compromising, and again where we see the benzenoid units are quite more when it is compared with the quinonoid units, indicating that. And UV also similarly, like, we saw the similar sort of responses. Overall we depicted a structure like where the benzenoid polar and with quinonoids is electrostatically stabilized with the help of the phosphate ions, like, which are available in the pH 7 buffer. So this is like the key thing. And later on, like, we found that once, like, we started digging out, like, which journal we start to see that we never heard that, like, a polyaniline was formed in neutral pH conditions and in electrochemically. So this is like first observation, and we also went for the patent application during this point of time, like, whereas we published the journal in Analyst 2013, like, found that it is very completely unique and unusual, like, which we also repeated several number of times, and we see the repeatability and reproducibility. And we found that, like, there is a formation of polyaniline, and as a tool, like, we just try to show that we can able to oxidize the ascorbic acid in various real samples. But as a part, like, I started to explore the various other aniline derivatives also in that moment. So in that moment, like, I saw that, like, one sort of important aniline derivative is like 1-naphthylamine, which is also considered as a carcinogen, cancer causing, and also, like, it can be able to generate or remove from the simple adsorption process by carbon nanotube. But whereas everyone discussed variously about, like, we can able to modify, but where here the concept is like value addition process, how this carcinogen is also can able to be converted into a good product or a sensor product, so such that, like, this study started. And whereas we found that, like, by simple adsorption process, it can able to this naphthylamine isomer can able to sit on the carbon nanotube, and whereas, like, at specific conditions, like 60 seconds is sufficient to cover up my entire carbon nanotube structure with pi-pi interactions, and over a specific optimal electrochemical conditions, I can able to see the similar polymer formation with 1,5 and 1,4 linkages. And where besides, like, we also try to see whether what is the role, and in the mechanistic view, like, we try to explore the other naphthylamines also, and we concluded that this particular aspect and this polymerization is only effective, and it can able to generate the polymer is entirely formed with the help of 1-naphthylamine isomer, because of the what is this para position of this amino group was blocked over here, but whereas it is freely available. And then we subjected for various other techniques and found that, yes, after adsorbed on carbon nanotube, like, we see enormous growth of polymerization, and again open circuit potential after just simple adsorption is also can able to give. But whereas we see one line over here at the top, like, it is going to a extent, like, where it will be reaching to a very higher electrical conditions, and where we found that that is like 0.395 volts, so which is completely depicting that the 0.395 volt is sufficient amount of energy or voltage is sufficient to generate this radical. And where when we are subjecting the the same 60 seconds of concept, and also like the 0.395 we are able to see that the polymer is formed over this carbon nanotube structures. And we also tried to expose the carbon nanotube modified electrode to various timings and found that 60 seconds is sufficient in order to see a proper adsorption over the carbon nanotube, and whereas like we further move ahead for the polymerization in neutral pH conditions. And then yes, obviously we also see similar characterization tools and found out that the outer surface of the carbon nanotube played a crucial role in order to see a surface grooves over different kind of places. Even TEM and also like the SEM also proposed the same, and similar to our polyaniline in the first paper, like where we saw the enhancement in the what is this like G peak, which is representing the sp2, and also we found that the benzenoid and quinonoid units are available in this particular platform. And also later on, like we also found that the evidences for the 1,5 and 1,4 linkages, which is completely a complete agreement for our mechanism. So that all information led us to go with, okay fine, we developed a sensor. And fortunately I just thought of like going for application as a sensor, electrochemical sensor, but whereas at that point of time I can see that the sensor which is developed over this carbon structure has been it was like completely, it is not at all giving any sort of response. So at that point of time we also noticed that like there is no response from different sort of bioanalytes like which are available in the similar pattern. And also we see a unaltered electrochemical what is the potential. So what we saw what we done is like we see we subjected the same electron to different pH conditions from starting from 3 to 11, and we found that the redox peak is like moving entirely in different fashion, like where it is completely agreeing the non-standard behavior such that like it can able to prove that like it is having a lot of potential to work as a pH sensor. Okay, again like this is like very broad spectrum, and again the conventional electrode system, and again I just try to explore different sort of carbons like but whereas I found that okay, multi-wall carbon nanotube is like giving a very good thing. But whereas I started to work on, I mean it's like carbon is of course like C stands for creativity, curiosity and all those things, right? So I started to explore like whereas like carbon it was like the bare carbon is like sufficient to means like with treatments like it is sufficient to select or detect this cresol which is available in the insulin derivatives as a what is this like a storage thing. And whereas we also utilize for the fish freshness like in order to see the difference in the uric acid, hypoxanthine and xanthine, and also like we also try to explore for the T sensor. So all these things, why can't we able to polymerize the same matrix over this pencil graphite electrode, which led us to think in that direction like during that span of time. And immediately I started to explore and also like would like to see that like okay 1 ml is sufficient, whereas we commercially or maybe like we try to do like in 10 ml or 20 ml of different kind of electrolyte systems. So within my ability like whatever I can do, so like I try to use the 0.7 mm pencil electrode, and where I just try to restrict the surface area with the help of this Teflon or whatever the things. And again like I just created with a low volume and try to repeat the same pH units with the DPV conditions. Why? Because DPV is like one of the excellent tool like where you can able to finish your task like within a stipulated time and very less fraction of time. So such that I can able to, I generated a calibration plot, and like whereas I see almost near to the instant response, like this calibration plot helped me to go with different kind of human sample analysis, like whereas you can see first of all I tried with the standards and how the pH is coming with the potential, and also like I try to see compare it with the what is this like normal pH sensor like which is common laboratory tool. And after that like I also try to see the how much error percentage. But whereas the beauty comes in like where as like I'm biology background guy also, like where we went to the what is this like chemistry, and particularly electrochemistry, like where we are working on interdisciplinary. So I try to use my own saliva, and we do not have this at that point of time like we should go undergo for blood sample, we need a chairing committee and so many things. I was in like hurry that like okay fine, I wanted to produce my paper, but I don't know that it will take a lot of time. Why? Because my seniors are accumulated at first point of time. So I just tried it at 25 years of old, like I was like right now I'm 36, but still this story is continuing. Okay, so at 25 years of old I started to explore different kind of stuff, like where my faculty my professor is also really impressed, like where saliva and tears and also the biomarkers. In the morning session someone is saying that like is there any way like while we can can try to think about the stress and all biomarker. Yeah, like during that span of time, I found that the pH of your human body is also like kind of a stress biomarker, like where it have an indirect approach, so such that we try to see, explore and everything. And later on, as a bio related guy, so I was like really interested with, where I just dropped like with bacterial growth sample. So what I done is like we well know that bacterial growth cycle, it's a very common experiment, like from our childhood we see for 24 hours, like we used to see the changes, and our life is also like this: death phase, log phase, lag phase and stationary phase. So I try to use the LB medium and also try to see how the pH is changed in over a span of time of 24 hours, like where I can see that during the bacterial growth, which is from the E. coli in the LS medium, like I see the release of acetic acid, like which is declining the pH, and I can able to sense, and which led us to go with the publication of sensors and actuators B chemical. But whereas again, as a assistant professor, due to limited things and all those things, we try to explore in different approaches, like where the similar polynaphthalate polyamine pyramid, we started actually to work on to see how the adulteration in the milk and dairy products. But whereas I can see this sort of we just ended up with a product like where we can able to go with the dairy products, and that also led us to develop a scientific reports to 2026. It is like continuous perseverance, like you can see starting from 2012 and now it is 2026, like whereas we try to dig like where we can able to bridge the gap. That is one important scenario, and that's the reason like I feel very special. Okay, fine, if you're really very particular about one work, and even in different capacities, like no one will stop you, and with a lot of collaborations and all those things we try to publish. But in the other vertical, what we done is like, okay fine, you're working on and you just try to make it like for 1 ml. What about the samples, like where it requires or it will lead only like in microliters? Okay, at that point of time we try to procure this sort of like electrochemical cell, which is like costing around $500, like even it is holding to 200 microliters. So at that point of time, out of curiosity, I started like to figure out why can't a punt of tube, like where we can able to make a 3 electrode system, so such that it will completely avoid the lossage of what is sample and everything. And I try to build myself with 150 microliters, and whereas like these are the conventional electrodes, you can see like how the miniature is happened. So with a lot of creativity, so I try to explore, and this also led us to go with a publication in Microchemical Journal, and with a model and light of uric acid, we try to see various electrochemical responses. And this is the reference electrode, so this is a pseudo reference electrode and working electrode, and again I try to use the same 0.7 mm pencil electrodes, and this led us to go with this miniaturization concept. But whereas still I am lagging behind. Why? Because we are looking for the active participants. Why? Because my area is not only limited to the polymers and also like the composites, but also I do work on different verticals, like where one of the hot topic is electro-organic synthesis, like which is completely different from the conventional robust organic synthesis, like where I can see the formation of organic products. You can see, of course we know that, but later on like we couldn't able to move further, that like whereas you can see the carbon atom which is having this iron impurity is also utilized for the conversion of this benzene to this 2-hydroxyphenols, like making like from waste to wealth. And also like I also like work on like pencil based electrochemical sensors, like whereas we used to define and modify within organic materials by utilizing the pristine iron which is available. And also like we work on the flexible sensors, like modification of various nanomaterials over this pencil and pencil graphite this papers, and also like different kind of foils, and that makes us to go with a flexible sensor. And also like this novel 2D and two-dimensional materials like MOS2, MOSC2, and also different kind of materials, like we also working in the similar lane for the supercapacitor application. So you can see like a normal pencil graphite electrode also sufficient enough to generate a suitable capacitance, like which will be having a impact factor. And now with some collaboration and all those things, we started to work on the carbon quantum dots enabled packaging films, like where these are considered to be biodegradable film. And still there is a lot of work is going on because of limited manpower. We are using MSc students to generate these sort of things. And at the end of the day, I just would like to say that again, this is like very one of my PhD scholar who joined recently, so he started to use this what is this, like bio waste or biomass which is collected and which is a agricultural waste, and and he tried to convert this waste to wealth as a slow release fertilizer, and here we end up in different verticals. And this way I would like to conclude, and if you need any further details, you can just scan this and you can able to see all my details and the publications and patents and the projects like whatever I acquired till now. And finally I just would like to conclude with a thank you due to the limited time. So hope I'm on time. Yeah, thank you everyone.
Shedding light on the importance of polymerization and their applications in today's times. Now may I please call upon Dr. Darshana Potfode from NMIMS Mumbai. Her research area includes advanced energy materials for energy storage, electrochemical energy storage devices, and electrocatalysis, as well as sensing.
Good afternoon, everyone. This is Dr. Darshana Potpode from Sunandan Diwatiya School of Science and MIMS. First of all, thank you organizing team and Chandra sir for providing me opportunity to deliver research what we are conducting at NMIMS. I'll be briefly taking you through the research activities what we are doing at NMIMS. So the research what we started with. So I did my PhD in DRDO. So the day one when I started working with them, the project was assigned. You have to develop so and so polymer, and that polymer you are going to utilize for energy storage. So then I started with the literature, like what kind of polymers can be used for energy storage, and till that time I was not aware about, because just the MSc pass out what he or she thinks about the research. So then I started with the polymer literature and got to know polymers are the more than materials, like they are the possibilities. So the art lies in between, like how you are shaping them into particular application. Then we started with like conducting polymers. So majorly in energy storage area, the polyaniline is the major polymer which is being used for energy storage. And apart from polyaniline, then thiophene, thionothiophene based polymers, then P dot polyethylene dioxide, again a thiophene derivative, and polypyrrole type polymers are being used. So the beauty of these materials is you can play with the chemistry and bring them into a particular composition or the morphologies and whatever the best required for energy storage with the high surface area. And then you can play with chemistry, a lot of chemistry to be done in the polymer side. But there is a limitation for these material to be used for to use as an electrode material. So how to overcome these limitations? Again, then we go with the composite formation, carbon material to provide them a mechanical strength, and then what is the extra parasitic reaction happening and which are leading to the degradation of material. We can come up with the problem solving thing, like you can blend with the carbon material and you can come up with the high energy storage capacity and high electrochemical stability for them. So with the fabrication possibilities, we can convert them into 2D, 3D shapes, and we can utilize them for energy storage. So motivation behind conducting polymer is like they have high specific capacitance compared to carbon materials, good electrical conductivity, safer than metal oxide to be incorporated in a commercial product. And then flexibility, yes, they do provide flexibility. So you can have flexible devices, prototypes can be fabricated using this. And the good point of the point to consider about them is like easy synthesis and fabrication as compared to other materials. They are lightweight, so that the weight of the total device can be we can maintain the light weights as much as possible by having redox additives into the polymers, and then you can have excessive redox reactions to have major energy storage contributed by them. So the good thing is accessible chemistry. You can play with chemistry, come up with the copolymer composites, or there are a lot of options for coming up with the high energy density supercapacitors as compared to the carbon based materials. So advancing electrochemical energy storage with a conducting polymer is one of the major motivation behind this research project. So how they work like a doping is required from them, as such form we cannot charge them with a positive negative charges, so dopants are required. So you can dope them electrochemically or chemically, and accordingly polarons, bipolarons, positive negative charges are being added into their polymer backbone, and then you can use them as a positive negative electrode for charge storage. So this is the possibility when you have in a general form without any dopant. So band gap, it's generally in the semiconducting form. So when you dope them and make them conducting with the help of doping agents, or electrochemically doping is also possible. So you bring them into conducting form, which is the conductivity can be brought down into metallic form. So against the chemistry, a lot of chemistry to play with. If you are adding excess of dopant, then you may end up with the less stability in the material. So this is how we play with the doping to enhance the charge storage in a polymer. And polymer based pseudocapacitors, generally there are three major types all of you must be aware about. So EDLC type, pseudocapacitor, and battery type. So we are mostly focusing on pseudocapacitor in this project, and this is how they store the charge. While p-doping, positive charges are getting created on the polymer backbone, and negative charge counter ions can come to store the charge, vice versa for p-doping and n-doping. So this is how we can utilize them as a symmetric combination and asymmetric combination, provided your polymer should be n-dopable and p-dopable at a time. If it is not, then you can have the other electrode in a carbon form to come up with a device. So majorly the polyaniline, when I started in 2012, so polyaniline was showing good charge storage capacity, but the problem was with the electrochemical stability. So if you go for a longer cycles, more than 5000 cycle, then the stability is nearly less than 70%. So the mechanical degradation was the main problem during charging, discharging, swelling and shrinkage was happening within the polymeric backbone, and that leads to the degradation. So, and when you compare with the metal oxide or a composite of polymer with metal oxide, they had limited practical capacitance, low conductivity and degradation if you are using as it is them. So overcome this limitation, what the practical solution should be. So we combine them with the carbon materials. So CNT was our first additive into the polymeric matrix, and you can see with the same images, polymer as such was forming a lumps, but when you have a multi-volt CNT into a polymer matrix, they tend to coat with a few nanometer thin film kind of film formation was observed, and with that fabrication technique we could achieve a stability of composite with. So here you can see 50% of polyaniline into with the multi-volt CNT. You can see a stable electrochemical performance throughout when it is used in a symmetric device combination. So in this way, with the multi-volt CNT, we could achieve good electrochemical stability for a polyaniline MWCNT composite. So further, if you are comparing the energy storage capacitance with the metal oxide, so the capacitance is limited to maximum 4 80 or to 500 farad per gram. So how to further enhance the charge storage in polymers? So there can be additional additives which can which can be a redox active molecule, and they can contribute additional charge storage to the polymeric material. But the chemical compatibility we need to consider here, how they can store the charge, how the combination of polymer and redox additive is going to work with the system. But in this study, what we learn is if you're adding redox additive in the electrolyte, they are leading to parasitic reaction, and then the chemical stability will go up. So what will be the solution for this? Then what we come up with a gel type electrolytes. So you cage them into a polymeric matrix and limit the redox reactions. So when we cage them into polymeric gel matrix, it was like a enhancement in a charge storage capacitance. Also, like you can have a stability throughout the electrochemical charge discharge cycles. So that was the one approach to improve it, and this is the performance we achieve from. So CNT as such is having interaction with redox active material, and then the polymer is also compatible with the redox active material generally. So if you test separately without a composite, there was enhancement, but when it is in a composite, so it was a synergistic improvement for the charge storage and as well as for the electrochemical stability. So next area we explored for this is a dendritic conducting polymer. So polyaniline as such, we can use it for supercapacitors, but limited charge storage capacity with the electrochemical stability is also very limited. So what we did is we planned a dendritic conducting polymer which will have a redox active centers, and then a typical morphology with a three-dimensional orientation, and then you can have a better electrode electrolyte interface to store the charges. So as these are polymers, they will be compatible with the organic electrolyte. So we tested them in organic electrolyte. So beauty of these polymers is you have a redox centers that will be contributing to the charge storage, and you have a thiophene sulfur nitrogen combination which is added to the carbon backbone, and that was like we could achieve more than 300 farad per gram with a quite stable electrochemical performance. And then we played with different thiophene moieties like selenophene, thiophene, and then we compared their performance with like each of the moiety what we added in the triphenylamine backbone of the polymer. And then we could see because of thiothiophene is the highest having highest charge storage capacity with 500 farad, more than 500 farad per gram. Since the charge storage contribution is more than one thiophene unit, so we had a good charge storage capacity for this thiophene option. Then we implemented that into a symmetric device, and we could achieve more than 45 farad per gram. So this is the device performance for polymer what we achieved. So next approach in NMIMS we are utilizing. Can I have a bottle? So what area we are exploring is we are recycling the polymers and we are converting them into a redox active MOFs, and that MOFs will be utilizing in polymer composite to further enhance the charge storage and stability. So the main problem with polymer is swelling and shrinkage. So if you are providing a space for a polymer to have a better swelling shrinkage option, so you should have some additives that will provide some extra space, as well as that additive will have a redox active contribution to the charge storage. So these are the MOF we are planning with the polymer composite. Initially we started with the recycling PET, and then MOF fabricated in an electrode combination, and then it is perfectly working for a charge storage capacity. So this is one of the area my PhD student is exploring, how to recycle volarization of plastic to convert into useful electrode material. And the other area we are exploring is COFs, covalent organic frameworks. A beauty of these material, you can play with the chemistry to have optimum pore size, high surface area, which is required for better energy storage. And with this, we have started with redox active covalent organic frameworks, and recently we have received a DRDO grant for this project. So we are actually exploring as it is in the form of covalently bonded polymeric form. And also there is another possibility to convert these COF materials into highly ordered carbon structures, and that carbon structure can be also utilized as a negative electrode for the supercapacitor charge storage. So positive electrode can be COF, negative electrode can be carbon derived from COF, and this is where we are playing with the material to come up with a high charge storage capacity and electrochemical stability. So in a recent review, we are come up with rather than using simple carbon backbone for a COF to store the charges, there is a limited scope for having charge energy storage or charge density. So if you are adding heteroatoms to the COF, that is drastically increasing your charge storage capacity. So you can play with nitrogen, sulfur, and other heteroatom like oxygen to come up with the high surface area, and this high surface area, high redox activities in the COF to have higher charge storage capacity. So this is where we are started with the COF material, and then you can see the redox peaks are visible in the COF when it is used as an electrode material, and when you are converting as a carbon material, you can have EDLC type charge storage. So we can combine them to have the asymmetric supercapacitor. So what are the challenges for this for us is like a multi-step synthesis for a COF. But once the COF is synthesized, you can have a variety of applications, like not only limited to energy storage. There are a lot of application can be explored with this, and then large scale production is also a limitation for us to come up with. And then optimization, if you are converting COF into carbonization, the optimum condition is very much required. These are the challenges. And with this, the acknowledgement, DRDO, yes, for providing us a research grant, DST Inspire Fellowship for one of my student, and then NMIMS seed grant, they made us available to work with. And this is my research team. They are working on energy storage technologies. With this, thank you.
Dr. Vinayak Kamble, Dr. Sonu Gandhi, Dr. Nandimalla Vishnu, Dr. Darshana Potpode.
let's have a quick lunch break. Before going to the lunch, we will be having a group photo outside. Those who are in the t-shirts, they are eligible to have the group photo. So we will reassemble here by 2:15. So please be there at 2:15 so that we can start the session. Already we are running late. So we will like to start the session at 2:15 sharp. Thank you.
Aisha Siddiqa, a postdoctoral fellow in the Carbon Lab and chair for this technical session. I take this moment to welcome you all to the last technical session of this conference, which is themed as Nature as a Blueprint, Engineering Intelligent Polymer and Carbon Interfaces. This theme sits at a fascinating intersection of material science, chemical engineering, and nanotechnology. We have a compelling roster of 4 esteemed speakers contributing unique viewpoints and meaningful insights to this session. Each speaker will have 15 minutes for their presentation and followed by 5 minutes of Q&A session. No Q&A again. Okay, no Q&A. I respectfully encourage all the speakers to stay within their designated time slots to ensure this session proceeds smoothly. So, first of all, I am pleased to introduce the first speaker of this session, Professor Rabibrata Mukherjee, sir, Professor of Chemical Engineering Department, IIT Kharagpur. His areas of expertise are thin film instability, soft lithography and nano patterning, colloids and interfacial engineering, surface engineering and coated materials, soft nanotechnology, super hydrophobic surfaces, and many more. With this introduction, I invite Professor Mukherjee, sir, on the stage to deliver the talk.
Good afternoon and namaskar, everyone. Chandra, thank you very much for inviting me. So it's a classic example that everybody is biased because I have nothing to do with carbon. But anyway, so good that young people are mostly having lunch and not many are here because my talk is something young people should not follow. Congratulations, Chandra, for completing 15 years. I have seen your journey, not from 2010, but from 2004. Instability Interfacial Science Lab, Hall 7, IIT Kanpur, and then from 2010 at IIT Hyderabad. And thanks for being unusually kind to me for no reasons. And while glancing through the older pictures, this is how we were. 2010, we just completed. All of us had more hair, less gray matter also probably. And I also came across this poster which made me very emotional because 5 years back, Chandra very meticulously during COVID time also celebrated 10 years of the lab. And we did miss Manish. We do miss Manish a lot today. And I'm sure Chandra will fondly remember him because if not anything else, you heard the word RF gel from him for the first time, which you have taken to a completely different level. So I will talk about something which has not much to do with carbons, but it's on patterns and surfaces and functionality and whatever. So some of you, there are posters and many of you know about super hydrophobicity, structural color and stuff like that. Topographic patterns, we are Bengalis, so Sandesh has come with nice design. These are also patterns. So you make Sandeshes, you sell them, you make nano patterns, you publish them, whichever way you look into. But there can be more complex patterns like any painting, any design is actually a chemical pattern. You can have, in fact, all microprocessors are chemical patterns of alternating domains and P and N type areas. There are a lot of this application of hydrophobic surfaces, self-cleaning surfaces, etc., etc. I don't have the time today to go in deeper. Structural color, they are all related to patterns and structures that are present on the surface. Anti-reflection coating, which are very, very important. Anti-reflection, anti-dust, self-cleaning coatings are very important in the context of solar panels, which are being installed everywhere. And the whole advancement in the microprocessor industry, computers, how fast they came is because of photolithography and how it has evolved over time. I will not go into the details of that, but there are limitations, I would say. Photolithography is a very specific technique for the microelectronic industry, and there can be many, many other application areas where you would like to have patterns available on different type of materials with not so much precision and certainly at not so much cost, so that you can do whole lot of things, including very fancy stuff these days people do, like point of care diagnostics and all this stuff. So that led to the emergence of this whole area of soft lithography in early 90s. George Whitesides and Stephen Chow, these are the prime movers. They started working. So there can be basically, again, I just reiterate, there are two types of patterns, chemical patterns and topographic patterns. The magic material for soft lithography seems to be cross-linked polydimethyl siloxane or Silgard 184. which or many people, everybody who works on microfluidics experiments and all these things, they have come to know about it. Easiest technique is basically, so this is what it is. It is like it comes in two parts, oligomer and a crosslinker. You mix them, it's a high viscosity liquid. You pour it somewhere or put it somewhere and you do a thermal annealing. There are physical crosslinks. So a soft liquid, soft high viscosity liquid transforms to a soft elastic solid. And based on that, the first soft lithography technique that was reported in a science paper was replica molding. So you have some patterns, you pour some Silgard on that, do a thermal curing, you get a negative replica, which everybody uses even today. Then there came another interesting technique from the group of Stephen Chow. Why the video is not working? It's in the slide. Anyway, so it's nano imprint lithography. So yeah, it's working now. So you basically take a glassy polymer, you heat it up above its glass transition temperature, emboss it hard, cool the material. Because of glass transition temperature, it becomes solidified. You take back the stamp and you get the negative replica of the patterns. So this is a 2-minute introduction of soft lithography, and if you are following that, you will realize that there are n number of techniques by which if you have a stamp, you have the possibility of creating a perfect negative replica. The question that, as everybody was talking about struggle in the initial years, Professor Murthy talked about it. When we started, the question was there was not adequate resources. I mean, some of the things, even with a very, very sophisticated fabrication lab, you probably can have access, but at many times you cannot. So first question we answered is that you have one stamp, and with that, can you create structures which have different feature height? And what we did was we sort of combined the essential physics of the transformation of a viscous material into a viscoelastic solid, into an elastic solid during thermal annealing. And what we did was tweaked was basically the concept that this transition is through different levels of viscoelasticity. And if a viscoelastic material is compressed, and then the force that is compressing it is withdrawn, that it undergoes some sort of stress relaxation. Again, a very well-known physics. And based on that, we could show that depending on the extent of pre-curing, right? So basically how elastic your film is, you can sort of control the depth of the patterns. And starting from a single stamp, we could eventually create multiple structures which have the same periodicity but different feature height on demand. Moving on, we sort of used a bit of chemical engineering knowledge that instead of doing this annealing in an oven, we put it on a slanted platform so that you can control the heat flux over there. And that means that there is a spatial gradient in the viscoelasticity of the film, and that eventually allows us to create a surface which has structures but with topographic gradient all along its depth. Basically, I always believe in that Pepsi advertisement, Dil Mange More. So once this was achieved, the question that we posed was, is it possible to now create structures which are taller than the original feature height? And the idea that came that when you use a sticking plaster and you peel it off, the part of your skin sort of gets pulled up just ahead of detachment. And we relied on that physics, but there is a lot of background to that. So the whole area in which Professor Sharma has contributed heavily in this area of contact instability between soft elastic films. So if a soft film, a rigid surface approaches, because of intersurface van der Waals forces, what you see on the right side frame is there are self-organized patterns that appear. So it's a flat surface, you are doing nothing, just a slide, glass slide, transparent glass slide from the top is approaching it, and you see a whole lot of structures gets created. So there are multiple, Professor Sharma was talking about multiple PRL papers, and multiple of these PRL papers are based on this particular theme. There's a lot of science behind it, scaling, etc., which I'm not going. But what is interesting is these structures are transient, and if you withdraw the stamp, the structures disappear. So what we also did was you can get these structures while the stamp is approaching, but you can also see the structures sort of following that reverse path when the stamp is withdrawn. This had been seen in several top-end papers, right, under an optical microscope, but no one ever cared to do an atomic force microscopy. And those of you who were present during the group photo, sir was pulling my leg with the AFM, because that's the only thing I learned at Kanpur, and I learned it so well that I could not learn anything else in my life subsequently. But we did something, and we for the first time did some measurement with the atomic force microscope of this bonding phase and debonding phase. And if you just look into the vertical scale bar, you see something interesting. Same features, but during debonding the heights are higher. So that means that because of adhesion induced some sort of hysteresis, you can say, the patterns are stretching to a higher height. And to cut a long story short, we now did the same experiments with some some pattern contactor, and during retraction what you see is that there is a grating pattern surface, nothing exciting. But please look into the vertical scale bar, it's 420 nanometers. 420 is also something, but the results are not 420. But the stamp which is shown in the inset had feature height of 150 nanometers. So that is what you could create. You had a grating of 150 nanometer. If you are following my talk, you will understand any soft lithography, standard soft lithography technique, most of which have been published in Nature and Science, will allow you to create a negative replica with 150 nanometer depth, but we were able to stretch it further. And then there are some chemical modifications, etc., etc. So it also coincided with experimental validation of some very basic understanding that the coefficient of friction at the nanoscale becomes a function of the contact area, which there was a Nature paper in 2011, which we were sort of able to substantiate. This is incidentally my last paper, I think, with Professor Sharma. This is well after I was in Kharagpur with my students also. Third one is a slightly different type of problem, but again we use the same concept of viscoelasticity. Again, this whole area started off with a Nature paper by I think Ned Bogdan in 2000. That is, when you thermally evaporate a metallic layer on a soft polymeric film, all of you remember this experiment of bimetallic strip, right? If you cool it down, it bends because of a mismatch in the thermal coefficient. Basically the same physics, but in a thin film geometry. And so when the film metal polymer bilayer cools down because of the interfacial stresses that get generated because of the thermal mismatch in the thermal coefficient, it leads to some self-organized wrinkles like this. And what we could show that again, by varying the extent of viscoelasticity of the substrate, you can play with the parameters and same film thickness just by varying the viscoelasticity, modulating basically the extent of viscous dissipation versus elastic, the stress relaxation. You can create structures with different morphology, which also comes with different wettability, different optical properties, etc., etc. If you are interested, you can look into my paper. And some of them actually give a very good anti-reflection property, as you can see from the inset of the figure. Moving on, the last work, again something like poor people do often. One of the very standard easy patterning technique is to get hold of a transmission electron microscope grid, place it over a polymer film and do some UV exposure or something. The whole idea is that as the film gets exposed to the UV, in areas between the grids, there is a depression that caused because of the local surface oxidation. This has been very widely used, and people have created some structures like what you see over here. And everybody thought this is a surface phenomena. So for example, I am talking of a specific example of UV ozone mediated surface oxidation of Silgard. People have created such structures before, and also it is also used for exposing this type of surfaces for modulating their wettability. So Silgard is inherently hydrophobic. Often UV exposure is done to make them hydrophilic. This is all well known. But when we started looking into it, everybody thought, I repeat, it's a surface phenomena. But for the first time, when we examined carefully, we realized that, the film thickness you take also has started to influence the depth of the structures or patterns you get. So eventually, no theory is available, so some sort of hand waving. And the argument we place that in a thinner film, what happens is the propagation front sort of, basically it has to compress a layer below, which is the compression is now sort of hindered between one propagation front and a rigid substrate below, right? So sort of it sort of gets hindered. In a thicker film, it doesn't really know where the bottom substrate is, so it keeps on deforming. And we did some careful measurements also, so it shows that beyond some time, it sort of gets saturated, all the chemistry and all that. And then my student, it was good that she did not listen to me. I told her, okay, you have got some results, let's publish maybe a bulletin of material science or something. But she decided that she will vary the cross-linker. And I was very certain nothing much is going to happen. But what came out was amazing. Just give me 2 minutes. That the depth you are getting is a non-trivial function of the crosslinker, or the vis-a-vis the extent of elasticity. So we started to dig our head what is happening, and what we did was we did a continuous atomic force microscopy of the same area over a prolonged period of time. And to cut a long story short, what we realized that if the film has higher level of elasticity, then this film, once the exposure stops, it now starts to undergo stress relaxation, and there is a virtual flattening that happens, and that leads to reduction of the depth of the features. So that's all what I wanted to show you. Conclusion, mostly these are very simple. I enjoy the fun, creative fun and the joy of science, but with this type of fun it's very difficult to get funds. So anyway, whatever it is, these are the people whom I should acknowledge, and this is a writing which I always love. It's there in front of cultivation of science. Science is the highest form of creative art. And not thank you, I just need a minute of sales talk. Firstly, we have, like IIT Hyderabad, we have a Sathi at IIT Kharagpur. Sir is not here, but it is during his time the program started. So we have one of the finest microscopes, a time of flight SEAMS and an UTM. So anybody interested, please write to us. You can use this facility because these are national facilities. The second thing is, it's a DST funded major project. There are right now 5 Sathi centers at IIT Kharagpur and IIT Hyderabad, both are Sathis. IIT Kharagpur is a first generation Sathi, like we are a first generation IIT. IIT Hyderabad is a second generation, but much better Sathi, just like a second generation IIT. Probably much better. Anyway, I don't want to comment on that and drag controversy. So amazing images, and I can proudly say now I have seen atoms. Second thing is, there is also an amazing program of Ministry of Education called Spark. Please care to look into the spark.iitkgp.ac.in. It's an international mobility and visitation program. IIT Hyderabad is a major beneficiary of that program. And there are these 12 themes around which we accept proposals around the year. And so it funds the travel of international faculty to India and Indian students abroad, right? So we are the coordinating institute. In fact, I am the national coordinator. So right now the program Spark is running in 120 institutes across the country, which makes it very, very inclusive. And very recently in early March, we had a conclave in Kolkata. Rohini will find herself somewhere in this picture. So thanks, Chandra, again for inviting me. Thank you very much for giving me the chance to talk to you. No questions, right? Very good.
So much, Professor Mukherjee, for the insightful talk. And now our second speaker is Professor Cherished Pramanik, Professor in the Electronics and Telecommunication Department at Indian Institute of Engineering Sciences and Technology, Shibpur. Her research expertise spans the areas of electrical biosensors, chemical sensors, and related signal processing with the aim to develop point-of-care devices. So I invite you to deliver the talk.
Yes. It's a challenge for me to speak after Professor Mukherjee. After going through all his mesmerizing pictures of AFM, mine will be a rather blunt slide presentation. Thank you, Chandra, for inviting, and congratulations to Carbon Lab for completing 15 years of the illustrious journey. So to fit myself into the theme of the program, so I precisely work on electronic and electrochemical biosensors. So graphene closely fits into the theme. So we have been working for some time on graphene field effect transistor biosensors. And what we do is we engineer the interfaces by either molecular imprinted polymers or by mixing it with MXene or by making some scalable development, which leads to ultrasensitive detection in clinical samples. That's the motivation. Right. So coming into the basic principle of operation of the field effect transistors, I think many of you are aware of. Like electrochemical transistors, these transistors also have 3 electrodes. We call them drain, source, and gate instead of reference, working, and counter. So gate electrode basically replaces the reference electrode with a different function, of course. And through drain and source, we have current flowing through the channel material. This is the channel material which is deposited either on any, you can deposit it on silicon, but if you have to think of affordable substrates, we have changed the substrate to PCB for integrability. Now, if we change the gate voltage, which is again a reference electrode or made of AgAgCl, then there is a change in the current through the channel. So that's called the field effect, because it's a transverse field for which the longitudinal current through the transistor changes, and this is precisely the devices which we have in all our electronic systems. So these devices can be actually exploited for use in case of biosensors as well, because most of the molecules which we want to sense, if they are charged molecules, they will sit on the surface of the wafer through some receptors, through on the material through some receptors, and those charges modulate the change in the transconductance. These are much more sensitive because of the intrinsic transconductance, which provides a gain to this type of sensors, and there is a possibility of real-time detection. But yes, there are various challenges which needs to be overcome and heavily addressed also as of now. The device screening effect, since it's a charge mediated problem, so the part of the molecule which is actually outside the device layer, because whenever a liquid comes in contact with a solid, there is a double layer of ions that is created. Now the molecule, the part of the molecule which is actually outside the double layer of ions, that does not change the charge concentration, carrier concentration within the channel material, and hence that part of the charge of the molecule doesn't come to use. So that's called the device screening problem. So various strategies have been adopted over the years. So I have a list of them. List of them which has been addressed. Now, just to make it short, whatever methodologies have been adopted so far for overcoming the device screening effect, they cater primarily to smaller sized molecules like the protein biomarkers, nucleic acids, neurotransmitters like this. Now we have an interesting group of molecules called extracellular vesicles or exosomes. They can be actually markers for early stage cancer detection, whereby we can differentiate. It has the potential for differentiation between healthy patient and a patient with just a benign onset of tumor. So these sort of molecules are heavily screened because of their large sizes, and what we have tried to address is make some arrangements to reduce the device shielding effect of these molecules. Other than the device screening effect, we do have the reliability aspects definitely as a problem of these materials. Like we have been hearing about scaling up. So making 10 devices and making 1,000 devices do not give you the same results. So we need to bring in various machine learning algorithms to cater to this sort of deviations, intra-device and inter-device deviations. And from the real-time detection aspect also, most of the time the detection is based on washing steps. So many molecules will not give you the general natural redox peaks. So we need to do a number of washing steps that hinders the real-time detection. And of course, scalability and the integrability are major aspects of it. Now, why we have thought of introducing magazine with the graphene oxide, reduced graphene oxide layer that we do? Of course, with the purpose of reducing the device screening. Now, making pores is definitely one way of reducing the device screening. I have the mechanism over here. So if we can make pores and the dimensions tunable to that of the biomolecules we want to sense, then if the biomolecules closely fit or if the pore dimension is slightly larger, then the electrical double layer which will be initiating from the surface of the biomolecules, they cannot completely form a shielding layer. So those starting from the surface of the molecule and those initiating from the surface of the pores, they actually collide with each other and we do not have a complete rigid shielding. So that's the idea of actually introducing pores into graphene. For that purpose, we have taken the help of magazine. There are reports of graphene magazine composites which are used for battery electrodes, which leads to porous structures enhancing the surface area. But the problem is over here, the magazine component is so large that it forms parallel sheets which can shunt the conductance of the graphene, and hence the transconductance effect will be lost. So what we need to do is optimize the ratio of the mixing of the graphene and the magazine so that They will be intercalated, but there will be no magazine sheet which will be shunting the graphene. So that sort of optimization had to be done, with which we actually started, because we tried to explore the development of the porous FET architecture on graphene using a graphene magazine composite, which has rather not been explored earlier. So the main features of the work that I am presenting here is, so we have adopted the scalable synthesis method of graphene magazine. We have tuned the ratio, did a number of experiments to select the optimum combinations, which will be suitable for the detection of exosomes, as well as it will maintain the transconductance property of the graphene. We have included additional features of dielectrophoretic based concentration, which doesn't require ultracentrifugation for the extraction of exosome from the blood samples. Another important feature is, yes, we have tested on the patient samples, developed on PCBs for the sake of affordability and integrability with the electronic circuits, and we have been able to differentiate between the normal patients and the BPH patients, which was actually our aim. So a very simple flow, we are patterning PCBs in our lab, around 60 to 70 chips can be made actually on a single PCB. We have made 3 such boards for this particular work. The graphene oxide and the magazine solutions are mixed in the varied proportions so as to keep the transconductance property of graphene intact, desirable. Then we heat it, thermally reduce it, the entire mixture, and then we can dice it according to the size of the sensor array that we want. These are some of the device characterization to support the development of the composite. So these are the different types of pore morphologies that we have obtained. Of course, the Raman shift shows that we do have multiple layers, around 7 layers of graphene. And with the help of some DFT simulation, we have seen that OH terminated magazine or fluorine terminated magazine do not have much difference in the interaction energies, and they are quite stable composites. Doing the XPS analysis also, we have been able to find out the binding between the titanium carbon, the titanium oxygen bonds. The BET analysis gave an idea of the available surface area. Now, those with the higher magazine concentration actually gave, though it led to higher pore sizes, but the effective surface area was less, which was probably because there was dense stacking of the magazine sheets, which ultimately reduced the effective area for the gas absorption. Yeah, we also tested the scalability part, that as I was telling. So we did a number of chips and measured the ACM port dimension in the ACM for the different chipsets, functionalized the antibodies. There is another important component in this work, that CD63 is one of the commonly used antibodies for exosome detection. So be it for breast cancer, be it for cervical cancer, the CD63 is a very common marker, so it's not cancer specific. So we had a collaborator related to this biomarker development. So they suggested to validate E2F5 actually. So E2F5 has been observed through our sensing system. It has been validated to give much better discrimination between the normal as well as the BPH samples. Yeah, these are some exosome characterization, biomolecular characterization of the exosomes. So typical term to tell the dimension of the exosomes in the range they lie. We have extracted patient samples from there for the sake of calibration. Initially, exosomes have been extracted by ultracentrifuge. This is a typical DLS and the NTA profiling of the exosomes that have been extracted from the patient samples. The Western blot over here shows what are the different proteins that make themselves appear on the surface of the exosomes. And since we are interested to validate E2F5, so we have actually in detail studied the E2F5 expressions for the different categories of patients. So DEP-based pre-concentration strategies. So with the help of simulation, we typically choose the frequency that will be suitable for exosomes varying from 52 to 50 nanometer sizes. To have PDEP, because the dimensions of the sensors is definitely much smaller than the dimension of the reference electrode. And this field is to be given between the reference, that is the gate electrode, and the shorted drain to source electrode. So since this dimension is smaller, we need to enable PDEP, that is positive dielectrophoresis force. For that, we need to do some pre-simulation. So these are simple COMSOL simulations we have in the microfluidics module. These are typical SEM images of the exosomes captured on the sensing surfaces with and without DEP, and histogram analysis of that. Okay, coming to the electrical sensing frameworks, out of so many devices that have been fabricated, it's not that all of them could be used for the analysis. We had to use depending on the reliable range of the Dirac voltage that was provided by the sensing devices. So we actually found out the variation of the Dirac voltage over the number of devices that have been fabricated. Then we started doing the calibration with different concentration of exosomes. So these exosomes were actually extracted from healthy patients. So in healthy subjects itself, there is an exosome concentration, something varying from 10 to the power 7 to 10 to the power 8 exosomes per mil. So we have actually extracted exosomes, diluted them, and made the calibrations to find out that whether we are being able to detect something down to 100 or 200 exosomes per ml, whether the detection limit or the change is sufficiently above the baseline fluctuations or not. These baseline fluctuations originate from the intrinsic noise of the device and also from the electrolyte sensor electrolyte interface. So going to the clinical performance, we had to compare the performance of these two markers. So this is the one which is not very specific, and E2F5 is very specific, though the level of the signals for healthy patients were somewhat close, but the differentiation capability of E2F5, so this is the green one. So the differentiation capability, there's a degree of overlap if you want to see for percentage change in IDS at a particular gate voltage, and for the shift in Dirac point is somewhat less. So that makes the classification better. But better doesn't mean that we can do the classification without any machine learning. We had to apply some machine learning because still there is a degree of overlap between the exosome count and the dimensions of a healthy patient and the BPH patients as captured by the E2F5 antibodies. This is a typical selectivity study which every sensor development group has to do. This is the patient recruitment table. So the patient samples were provided from PG Hospital in Calcutta, and the patients were recruited based on the absence of any other co-infections. So this is the typical clinical performance based on the machine learning model. And those who are into it will be knowing, no need to explain these graphs. We have to find out what is the actual concentration versus the predicted ones, and what is, and how we are being able to classify, what is the classification accuracy. So this is a small prototype where we have not yet embedded the machine learning algorithm yet. This should run. Yeah. So this only has the electronics part, that is the interfacing of the sensor, which reads the current of the FET device, converts it into a voltage, interfaces it with the microcontroller, and just gives you the reading in terms of the resistance of voltage. So it is only this much. We have not yet integrated the machine learning because it's not yet complete. So just working on 30 patient samples or 20 patient samples is not enough. So we are presently trying to scale this up through a translational project from the iHub of IIT Delhi. So let's see where it goes, and then we'll be finalizing the electronic circuits. We had a large group of collaborators for this work. So Sriparna, everybody is known over here. I mean, the first two authors are very much known. They are my co-members from INEAS also. And my biochemistry collaborator was Professor Shangomitra Sengupta from Calcutta University. And we had the medical doctor from PG Hospital who has provided us with the samples. How much time is left? It's over? Oh, 5 minutes. Okay, fine. So we have also tried to develop, for the sake of removing or reducing the device screening effect, the wrinkle graphene. So this is not, of course, our not new idea at all. Wrinkle graphene was reported in Nature Communications in 2020 by Professor Rashid Bashir's group for detection of nucleic acids once again through the CVD route. So we tried to basically figure out whether we can have something alternative, some scalable approach, because they also themselves have mentioned the problem in scaling up the formation of the crumple graphene structures through the CVD route. So we tried to follow the silver nanoparticle based deposition approach. We take a glass coated with silver to an aniline to get different morphologies of the deposition of the silver nanoparticles through optimization of the temperature and the time of deposition. And after that, we deposit the graphene oxide solution. We are procuring the graphene oxide solution commercially. Then we have also optimized the thermal reduction process in our lab, so thermally reduce it. And what we expect is that graphene oxide sheet is going to follow the morphology of the aligned silver nanoparticles, self-assembled silver nanoparticles. So these are some of the, so I do not better speak about the images. You all have seen such wonderful images. These look rather blunt. Anyway, we have picked up the optimum morphology depending on the dimensions because we wanted to explore the same exosomes from the prostate cancer patients here also. This is the contact angle measurement of the optimized surface. We check its robust nature by exposing it to artificial plasma, which doesn't have any exosome. So after contaminating with exposing it rather to artificial plasma from around 6 hours of time, how much the current degrades. So it has started degrading beyond this 4 hours. So of course this time is good enough because our measurement takes only 30 minutes. So we wanted to do this just to confirm that within the time of the measurement of the actual patient sample, the sensor current should not start degrading even in absence of any target analyte. So with the help of this surface also, we have been able to differentiate between the groups of the patients that we have been targeting. So these two were primarily targeted for bigger molecules like exosomes. Now, what we wanted to do is also something for smaller molecules. In smaller molecules, already a lot of work has been done related to the device screening problem. We sort of explored how MIP can be, if we interface MIP with graphene, if we can get anything interesting. Now we selected serotonin, a commonly available neurotransmitter. Actually, I had a collaborator at that time in the health science department. She asked me to do with serotonin. So they were developing the MIP for us. We were depositing on graphene and trying to find out how it changes. The interesting part over here is since we have a template created, and in the region of the template, like where the serotonin, the target analyte is supposed to come and bind, that molecule binds closely to the graphene surface than what we can get using antibodies or aptamers because they are a distance away. So here in case of MIP template, we can get a binding directly to the graphene surface, and that's what led to an interesting noise spectroscopic characteristics which we extract from the quasi-static current readings, current measurements. So from the noise spectroscopic characteristics, actually, just in case of serum, just in serum without the serotonin, that creates some sort of a hum in the higher frequency range. When we have the target analyte, interestingly for serotonin, it was observed that there is a bulge appearing, which got magnified. If you just multiply this data with frequency, it gives a much prominent peak. It starts appearing, a bulge starts appearing at a lower frequency, which is characteristic of the presence of the target molecule. So this actually helps us to say, even without involving any washing steps, that whether the target analyte is present or not. So I'm not sure whether this is going to work for every molecule. The reason behind this, we tried to explore doing some electronic band simulation studies. We found that some traps are being generated, specific traps are being generated in the band gap of the reduced graphene oxide, which is attributed to this sort of a hardness in the characteristics, the Lorentzian characteristics. Yes, these two we have validated with the number of patient samples and checked the data with the HPLC. The funding support that we got for this part of the work, especially for the exosomes part of the work, and the students who have contributed to this part of the work. So, questions by email.
For Professor Mukherjee and Professor Cherished with the coffee table book.
No problem.
मुझे भी पहले मैम पहले इंट्रोड्यूस कर दीजिए कनेक्ट
Yes, now we move on to our next speaker, who is from our own institute and a very close collaborator of our lab. It's Professor Mudrika Khandelwal from Material Science and Metallurgical Engineering Department at IIT Hyderabad. Her research spans interdisciplinary work enabled by knowledge of multiple disciplines spanning a wide range of applications such as cellulose composites, drug delivery, energy storage, materials inspired from nature especially, which is most relevant to this session. So I request you to take on stage.
Everyone. Welcome to the last but one talk of the C15 summit. And first of all, I want to say sorry that my daughter has been pleasantly entertaining everyone in between the talks. Yeah. So thank you, Chandra, for the invitation and for putting together entire schedule and the entire team that has worked very hard with him. I'm going to talk about one aspect of the various things that we do in our lab. We primarily focus on nanofibers derived from bacteria, which is bacterial cellulose. And if you look at that spin wheel on the right hand side, you will see we work on energy, healthcare, environment, and various advanced applications. What is bacterial cellulose? Cellulose, we all know, it's the most common naturally occurring biopolymer. And most of the time, or all the times that we see, it is extracted from plants and trees. However, my interest lies in cellulose derived from bacteria. The reason look at bacterial cellulose. Slide is not changing. Okay, no problem. Yeah. So if we look at bacterial cellulose alone, it is 100% pure. When you take plant celluloses, you have to use a lot of chemical processing to remove lignin, hemicelluloses, and so on. It's nanofibrous as produced in nature. It has a three-dimensional, highly porous network. So as produced bacterial cellulose, if you look at it, it's a hydrogel which has only 1 to 2 weight% solid content. But still it's quite tough, easily workable, and so on. So you can imagine that it is actually composed of nanofibers which are very, very long, nicely interconnected into a three-dimensional, highly porous network. It has very good mechanical properties owing to the high crystallinity. In polymers, we typically do not talk about crystalline polymer, but this is one which is highly crystalline, typically above 70% crystallinity. Sustainable biodegradability, that biocompatibility, that is a given. But what is also very interesting is when we look at the in situ tunability. The reason is that when you make curd at home, you boil the milk, you cool it down to slightly above room temperature and add old curd to it and allow it to grow and multiply, and hence at the end of the process you will get curd. It's a very similar process we do. We take all the rotten sugar juices or artificially made media, which is HS media in this case. You put bacteria in it, let the bacteria do its work, and at the end of the process, you will get bacterial cellulose. Why I say in situ tunability is because you're growing it tabletop. Trees, we are not growing tabletop, so you cannot tune the properties of cellulose which is coming from trees. So that's what makes it exciting to me as a materials engineer. How do we make it? So at the top, you can see the synthetic media where there is nothing but a lot of sugar. So what is this bacteria doing is ideally, or in a blanket word, it is polymerizing the sugar that is given to the bacteria into cellulose. But not just the synthetic media, one can also use the various fruit juices, which can also be utilized when you have a circular agrotech that you want to pitch for, because you can use vegetable waste, sugar waste, fruit juices, ferment them and get bacterial cellulose. So Why bacteria makes bacterial cellulose? Not for fun. What it would do for fun is consume sugar, would like to multiply, divide, increase its population. That is what it would like to do. But this particular bacteria, which is Acetobacter xylenum here, various other names and species are also there. Once it has consumed the dissolved oxygen in the media, what does it do? It wants to go to the top at the air liquid interface to get the oxygen supply from the top and have the media also from the bottom, which is the food, and hence it needs a boat for itself, and it starts creating exopolysaccharides, which is nothing but cellulose here. So this is what bacterial cellulose looks like. You can see, you can easily play around with the forceps. It's a very dilute hydrogel, but yet very workable. And yeah, it's a very slow process. We typically culture them for 14 days. Just to give you an idea why I'm calling it a very slow process. Most infection causing organisms which divide between half an hour to 3 to 4 hours. So you would have the infection spreading very quickly, but this one is very lazy. It divides only once 8 hours, and hence we have to go up to 14 days. As I mentioned before, there are lots of possibility to in situ modification. So if we are doing modification before the synthesis, that is during the media, we call it pre-production modification. But one can modify during the production as well. So start giving it some agitation, some templates, some other kind of electromagnetic gradients and so on. And most commonly practiced strategy across the globe is post-production modification, while my group focuses quite a bit on the earlier two as well. When I say modification and tunability, to me as a materials engineer, it means that I want to tune density, porosity, fiber diameters, pore size distribution, crystallinity, degree of polymerization, composition, and so on. Why? Because it would affect all the properties. Some of them I've listed below, like permeability, swellability, mechanical properties, holding capability, and so on. And another beauty of this material is that if you look at this diagram, you can see that bacteria exports polyglucan chains. So few chains of polymer of glucose come together to form a fibril, elementary fibril. Few fibrils come together to form a nanofibril. Many nanofibrils come together to form a microfibril, which is still in nano dimension, but it was called microfibril from the history. So it is still continuing the same nomenclature. And it assembles to form a network, three-dimensional network, which is composed of ribbons. So you can see a beautiful nano-structured hierarchical organization that the bacteria is already doing for us. And there are avenues during production that you can manipulate the bacteria or the environment to yield the properties that you would like for your application. I'll come to one application for today's talk, but let me also talk about another feature of this material. So if we look at the cross section, so the pellicle would grow at the air liquid interface. If we take the cross section, we start seeing a layered structure. So what we understand, the bacteria, not one bacteria, bacterium, no, bacteria come together to the interface, start building layer, another layer, and so on. So it's a layered deposition that is already happening in the nature by the bacteria. And this is how the microstructure evolves. So you can see on your very left, the first continuous film that is obtained at the air liquid interface, which is obtained in 2 days. Now, conventionally across the globe, all practitioners of bacterial cellulose would work with bacterial cellulose made from 14 days. What we took a lead in our group is that we started understanding the properties of the hydrogel, which happens before that. And it was very interesting to see, and we coined the word FFF in the literature, first form film, where we say it's a 2-day where the first continuous film is formed. Now, if you see the change in the microstructure, I'm sure all of you can see that in the first microstructure, the fibers are much more individual in nature. And as the time progresses, there is a lot more aggregation that happens. And it will not be surprising if I say the fiber diameter distribution changes, which I'll show you later. So let's come to some of the applications. And today I'm going to talk about only one application, which already we are talking about nature as a blueprint in this session, and I'm already talking about how bacteria makes, I call it the little weaver. It's making a non-woven fabric for us. But let's take another inspiration, which is silk. And why silk is so special? It is one of the strongest naturally occurring fiber. And why it is strongest and also one of the toughest is because of the combination of the orientation of the crystalline component and the amorphous component that is there, which gives it the property. So the idea is, can we make better fibers from bacterial cellulose? And why should I think about that? Is because if you look at cellulose nanocrystals, now, nanocrystals, remember I already said this is one of the crystalline polymers. So if we take nanocrystals, the modulus is calculated or expected to be 140 gigapascals, which is very, very high. Tensile strength of 6 gigapascal. Now, the magic would be if I could orient all the fibers, all the mess that the bacteria has created into a direction and make fibers out of it, they would be extremely good in properties. Where would you use it? Lots of applications. So currently use strategy, because when I say cellulose fibers, you all must say it's not new, because cotton fibers are nothing but cellulose fibers. But current strategies which are being utilized involves that you will dissolve the cellulose. When you're talking about dissolving the cellulose, you're destroying its crystal structure and you're regenerating it, converting it from cellulose 1 structure to cellulose 2, because that's thermodynamically more stable. So the idea here is, can we retain the cellulose 1 natural structure and make oriented fibers? So as anybody would do it, take fibers, stretch them, twist them, voila, the fibers are ready. So we did that for 14-day cultures, and you can see the properties. And just to mention one property here, we got about half gigapascal in the tensile strength, which is far, far away from what you can actually expect to do. So what should you do? Before doing what we should do, we started studying the rheological properties of the hydrogel of the 2 days. So 14-day and the 2 days. This is the rheological behavior for those of you who have not come across this technique before. It's simply to understand when a material is more stretchable, rather than when you let go the force, it will come back to original. So gel behavior versus viscous behavior. And what we are ideally interested is the cross section, the crossover point of G prime, which is storage modulus, G double prime, which is viscous modulus, should happen at lower yield values, lower stress values. So you can see the green plot versus the red plot. The green one, which is for day 2 hydrogel, which was much more dilute, more individual fibers, it happened at lower stresses. And you can look at the yield points also. We have quantified it here, which is much lower for 2 days. And hence, when we made fibers after 2 days of hydrogels, we could get much better properties. The modulus was better, and the combination of toughness and strength was much better here. And just to put this in a perspective, this is the performance and benchmarking in terms of a materials property web. You can see silk is the black dot there on your left curve, which you can see on all the 5 parameters: stiffness, strength, tenacity, specific strength, and toughness. You can see the fibers from 14 days, which is the green, and look at the fibers from first form film, which is 2 days, which is the red. We can see that overall the properties are much better achieved and closer to the native state for the red curve. Where does this fit in the entire spectrum of literature? You can see on the right hand side curve that various methods which have been used for spinning of bacterial cellulose have been plotted here, and the properties obtained here were much better. Only and only because we are using a much more dilute structure, which bacteria was already giving. It was only about listening to it and harvesting at the right time, stretching and making fibers out of it. I'll pause here. I made a blank slide here because I thought if there's time, we'll move on to another aspect, but I'll stop here. Any questions? Happy to take over email or now? Email. Thank you.
Carbon Lab. Dr. Srinath Mataparthi, he completed his PhD in 2019 from the Carbon Lab, and now he's a senior manager in Karnavati Innovation and Incubation Foundation. It is a truly special moment for the Carbon Lab to have you as a speaker, sir. Please take over the stage.
Opportunity to present my association with Carbon Lab started way back in 2012 during my master's and followed my PhD in 2019, and currently I'm associated with Karnavati Innovation Incubation Foundation, and I deal with startups and innovation. And I understand this is, I'm not going to talk about Canna Indica more, because I understand the moment when I talk, half of the audience will go out because they'll be listening to this since pretty long time. And today I'm going to talk about something really, really inspiring innovations. Okay, so the main objective of this talk is So the main objective of this talk is to give advice and motivation to the younger generation to say that there are pretty lots and lots of ideas available in the nature, lying inside the nature. All that you need to do is observe them, identify them. All right. So see, the thing is, like, any real-time complex problems can be solved by nature inspiration. Okay. So how do we, so what do we do learn from nature? So nature doesn't use any complex heavy machines or toxic chemicals to solve any complex problem. They just use the designs, textures, surfaces, biodegradable materials, and so on. And how do we biomimic, and how do we develop nature-inspired solution? We are not just copying nature, we are trying to understand the language of nature, we are trying to understand in the mechanism of the nature, we are trying to understand the process of nature, how does it really work, and trying to replicate the similar phenomena mechanism in artificial materials to solve real-time problems. Okay, as I said, I'm going to talk, it's not technical talk, I'm going to share some of the real life examples and nature inspired solutions, how innovations have inspired from nature, how these innovations has translated from nature ideas to market ready products. That means inspiring from nature, they have developed a products which are there in the market. Okay, coming to the first problem statement, that you see this forest fire everywhere across the globe. Okay, and once it got lit up, the spread over the forest fire it's massive. So current technology or methods that being used to suppress, to stop this fire forest is basically they use high equipment, which is time consuming and lot. Okay, inspiration from this particular biological material called pine cone, which comes from pine tree. So the beauty of this pine cone is You can see scales over here. These are under normal condition. These scales are tightly bound to the base material with the help of a glue. And under these scales, you have seeds inside. And the moment when fire catches the scales, whatever the scales are there, they just come up, open up, and the seeds, whatever the seeds there inside the scales, will come down, and therefore regeneration of this plant occurs. Inspiring from this particular biological material, the startup, which is Spirey, has developed similar material which detects fire system. So here they actually coated like wax material which is inspired from pine, where the moment when fire catches up, these wax materials will melt down, and eventually there occurs some chemical reaction which basically send radio signals to the nearby location so that we can easily stop the fire spreads up massively. And coming to the next example or real-time problem, extraction of rare earth metals elements is really difficult, which is time-consuming process, as also high equipment is required. And whereas this is one of the biological material which is inspired, which is called mussels. Okay, these mussels on the top of the shells, it consists of nanocrystals, okay, cellulose nanocrystals. The beauty of these nanocrystals are it has negatively charged ions. The moment when it interacts with positive charge ions like neodymium, it will attract and it will extract the ions. Okay, and followed by one of the major problem that majority of the countries are facing about filtration of microplastic, which is a major task. Okay, inspiring from this particular plant called redroot plant. So the beauty of this plant is it has biofilm in its roots. These biofilm, it consists of bacteria, fungi, and algae. The moment when any microplastic interacts with this particular roots, it will intact, and inspiring from this, they have developed, this particular startup has developed Polygon, a similar mechanism taking inspiration from this aquatic plant. And coming to another major problem for majority of cosmetics and other things, synthetic colors being used, right? And which consists of plastic, metals, and so on. And the moment it interacts with water bodies, the aquatic animals it's actually determined to both planet as well as aquatic animals. So here,
scientists have found a way to make all sorts of colors from just one ingredient: cellulose. Cellulose is the material that gives plant structure. It's not toxic, it's biodegradable, and it could even be extracted from agricultural waste. Plants use cellulose to make colours too, and animals use a cellulose-like material called chitin. Scientists from a company called Sparkcell studied the way that marble berries produce a deep metallic blue by bouncing light around spiraling layers of cellulose fibres. By replicating these spirals and spinning the material slower or faster to make the spirals expand or contract, the scientists can change the way that light is reflected to create different colours with different effect.
All right, so this is about how we can make structural colors through cellulose nanofibers, and which is, I think, better used for means like Madhika ma'am's research topic. And one more example from nature, which is a plant called ant tree. So the seeds of this particular plant, actually, whenever there is a wind flow, and when there is no wind flow, these particular seeds actually drop down from the tree. So when there is no wind, even these particular plant seeds actually travel a lot distance with a freely flowing with no wind energy is required. Inspiring for this, these scientists or innovators have developed such windmills, so which basically create more energy. All right, and coming to lotus leaf, we have been hearing about lotus leaf a lot. It's super hydrophobic, it's self-cleaning, and blah, blah, blah. Okay, but here we have many things to explore with the lotus leaves. So here, this is a postdoc work. So we have got beyond water, how it interacts, how lotus leaf interacts with various liquids. You can see in the video where it has been tested with ketchup, chocolate syrup, as well as the most viscous liquid, which is cosmetic. And the beauty of this leaf is it actually repels all these liquids. And we have almost done 25 different liquids. You can see how the droplets are in spherical form. Likewise, there is another work, postdoctoral work. So where we have identified a periwinkle flower, and we are able to create similar mechanism of superhydrophobicity from hydrophilic to superhydrophobic. So in this area, you can see this is a cement surface, which is basically a hydrophilic in nature. The moment when you have to adopt this technology and all, we are able to make it super hydrophobic. I'll just take a minute of this to ask in the audience. So what is one letter in our alphabet, worry, which is worrying letter? The moment when we heard about those words starting with that letter, we feel so worried and about. So anyone in the audience? The letter from the alphabets, which basically creates worry, so worried about the moment when you heard about that particular words. Absolutely, it starts with why, when, what, where, and who. Okay, it's taking an example. It's a better way. How? Wow. Yes. Wow. Yes, ma'am. So, and if you understand these W words, you're able to crack anything. So give an example of lotus leaf I just talked about. What is lotus leaf and so on. One more. Okay, apart from research and professional life, anything you're worried about personal life starts with W? Sorry? Some I heard. It's woman. Okay, anything last, any other word? Wife, right? So especially for men, so it is major concern. So the reason why I'm relating this topic is, so the moment when you understand the W words, because the direction of women thinking and men thinking is opposite direction, the moment when you understand how this actually works. Similarly, research is also in a way that you need to understand a different direction. All right, so yeah, W is a wonderful word. And finally, I'd like to thank my guru, Dr. Chandrasekhar Sharma, for inspiring me and giving me this opportunity and introducing biomimicry for this. And also Dr. Sriharita Rautu, who is my postdoctoral supervisor, who is actually continuing my research in terms of bioinspiration, biomimicry. And finally, yeah, to solve big, start building small. Thank you so much for giving me this opportunity.
Yeah, thank you so much, sir. Now I request you, sir, to felicitate them with the coffee table book. Ma'am, Mudrika ma'am and Srinath sir, please come on the stage.
I'm trying to make understand.
As we conclude this session, we look back on a set of deeply engaging and insightful discussions highlighting the design of intelligent materials and interfaces, along with some fascinating perspectives on the nature-inspired materials. Each of these contributions was meaningful, bringing diverse perspectives and valuable contributions centered on this session theme. I would like to sincerely thank all our speakers for their insightful presentations, and it has been a pleasure chairing this session.
As we come to the closing of this 2 days summit, C15, the Carbon Future Summit, I know many of you are in hurry to leave for the airport, have some flights. So it's time now to declare the winners for the poster competition. We have total 20 posters from different groups. And we were having, thanks to the evaluators who have done the very thorough job. I must thank all the 4 evaluators, Dr. Amritya, Dr. Rohini, Dr. Veda, and Dr. Anil. And they have come up with the final winners. So let me invite the winners for these poster prizes. So third prize is joint. So Atira Prakash. May I request Prasastha Sharma to come over the dais and present the certificate. Certificate. Yeah. Atira. Give that now. Next, third prize, which is shared, Vikas Mahendra Sharma. Vikas Sharma. Second prize for the in the Best Poster Award goes to Fatima Sanuva. Yes, you can take. Yes, you can take. And the first prize goes to Kiran Kumar Garlapati. Kiran Kumar Garlapati. Oh, he was not expecting it. Okay, with this, let me thank once again everyone who have come and shared their thoughts, and especially thanks to our alumni who have come all the way. And every good thing comes to an end, and that's where we are here now.
It's not ending.
What is it?
I have to say something. Yeah. So thank you once again, but we cannot end without giving return gift to Chandra, who actually organized this wonderful conference. So may I now invite Diksha. So as Professor Sharma always mentioned, the senior Sharma always mentioned the invention and innovation ecosystem. I think this is a perfect gift. Yeah. Yes, Lakshmi.
Actually, she's the real Lakshmi, like another Lakshmi.
Yeah.
Kids हैं क्या? बच्चे हैं? I now request all the kids to come on the stage. All the kids. There's some surprise for the kids.
They're sleeping there.
Chal. Pen drive is there.
This is his pen drive.
Yes, yes.
Yeah, that is mine. You can just play that.
Thank you, Srinath, for creating these beautiful memories. So with this, I would like to conclude the summit, and we can have a group photo with all Carbon Lab family members. Thank you, everyone. Yeah. Come quickly, all them. All students, all everyone.
You are still the student?
I'm still the student.